How do packing houses move watermelons, apples, and mangoes from field to store with stunning perfection? One bad drop or one missed bruise can turn perfect fruit into waste fast. In this video, we follow the full journey through washing until and packing, revealing the critical checkpoints and machines that decide what ships and what gets rejected. Watermelon slice candies are made by building a flavored sugar gel, shaping it into thick sheets or wedge forms, drying it to a defined chew, then finishing it with a sugar coat that gives the familiar grainy surface and prevents sticking. Production starts with the base syrup because every later step depends on solids level and water activity. Granulated sugar is screened to remove clumps and to keep crystal size consistent. Glucose syrup is stored in jacketed tanks so it can be pumped at a steady viscosity. Water is filtered and tempered because temperature affects how fast sugar dissolves and how stable the cook is. Acid powders and salt are staged in microfeeders because small shifts change sour balance and also change gel strength. Colors and flavors are staged as concentrates, so dosing stays precise when the line runs at high speed. A clear sugar solution is prepared first. Sugar and water enter a dissolver with strong agitation so crystals hydrate without settling. The dissolver runs until the solution is fully clear because undissolved grains can seed crystal growth later. Strainers remove any stray solids that could trigger graining or clog injectors. The clear solution then feeds a cooker where heat drives off water and raises solids to a target level. Cooking is controlled by temperature and residence time rather than by appearance. The goal is a repeatable solids concentration that will gel cleanly and dry predictably. If solids are too low, the candy dries slowly and stays sticky. If solids are too high, the gel sets too firm and can crack when cut. Glucose syrup is metered into the cook as a crystallization control tool. It reduces unwanted graining and keeps the final texture smooth rather than sandy. Once the syrup reaches target concentration, it is cooled to a blending temperature. Cooling is staged through heat exchangers so the syrup remains fluid but no longer threatens sensitive ingredients. Acid is usually not added at peak heat because low pH at high temperature accelerates inversion and can change chew. Instead, acid is added after cooling as a solution for rapid dispersion. pH is checked because it influences flavor brightness and also affects how some gel systems are set. The gel system is prepared in parallel because it needs hydration time. Many watermelon slice candies use gelatin as the primary gelling agent, sometimes supported by starch or other hydrocolloids. Gelatin is bloomed in cold water, so granules swell evenly. It is then warmed gently until it becomes a clear solution. If starch is used, it is hydrated as a slurry and then cooked to develop viscosity. If other hydrocolloids are used, they are dispersed under high shear to prevent fisheyes and clumps. The cooled syrup and the gel stream meet in an inline mixer. The mixing goal is uniformity without air entrainment. Air bubbles create weak zones and cause cloudy spots in a translucent candy. Static mixers are often used because they create strong folding without whipping. The blended mass becomes a hot, viscous liquid that will set into an elastic gel as it cools. Flavor and color are added late. Watermelon flavor is usually a blend of volatile components that can be stripped by heat, so it is injected after the syrup has been cooled into the safe range. Oil-based flavor components are emulsified or carried so they disperse evenly. Color is added as 2 or 3 separate streams because the finished candy needs distinct layers. A typical slice has green at the rind, white as a thin buffer, and red or pink as the main body. Black or dark inclusions can be added to simulate seeds, but many styles keep a clean surface and rely on printing or speckling in the red layer. To create the layered look, the line either runs sequential casting into one mold or runs separate sheets that are laminated. In sequential casting, the green layer is deposited first into a flat tray or onto a belt. That layer is allowed to partially set so it can support the next deposit without mixing. A thin white layer is deposited next and partially set again. The red layer is deposited last and forms the bulk thickness. Timing is critical because if the first layer is too liquid, the colors bleed. If it is too firm, the layers do not bond and can delaminate later. In lamination-based production, each color is cast as its own thin sheet and cooled to a gel stage. The sheets are then brought together in a laminator that presses them into a single composite slab. Pressing must be firm enough to eliminate air at the interfaces. It must not be so firm that it squeezes layers unevenly. Lamination gives strong layer definition and allows each layer to be tuned for thickness more easily. Once the slab is formed, it is set and pre-dried. Setting brings the gel network to strength so it can be handled. Pre-drying begins moisture reduction so the slab can be cut cleanly later. In starch-molded systems, the candy sets in cavities formed in starch. But watermelon slices are often made as slabs because wedges cut more efficiently from a sheet. Slab setting is done in controlled air rooms where temperature and humidity are managed to avoid sweating. Drying is the step that creates the final chew. Fresh gel has more water than the finished candy. Drying moves the candy into a narrow moisture window where it is elastic and bite resistant without being sticky. Airflow removes moisture from the surface, and then moisture diffuses outward from the interior. Drying must be slow enough to avoid case hardening. Case hardening creates a tough skin and a soft core. The line uses staged, humidity, and temperature so the surface does not seal too early. As the slab dries, it becomes firmer and more cut stable. At this stage, seed effects can be introduced if the product uses them. Seeds can be small, dark sugar bits that are added during the red deposit. They can also be printed later, but printing is less common on sugar-sanded gummies because the surface is rough. When seed bits are used, they must be dry and stable, so they do not bleed color into the gel. After drying, the slab moves to cutting. Cutting begins with edge trimming because slab edges often have thickness variation from casting. Trims are collected for controlled rework depending on the recipe and moisture state. The slab then passes through a strip cutter that makes long bands at the width of a slice. A second cutter stamps or slices wedges from the bands. Wedge geometry is defined by the cutter profile and by the band width. Cutter speed is synchronized to belt motion, so piece weight stays consistent. Cut quality depends on slab temperature. If the slab is too warm, it smears and sticks to blades. If too cold, it can crack at the layer interfaces. Many lines use chilled, but not cold cutting conditions to get clean edges without fracture. Blade coatings and blade wiping systems reduce buildup. Some plants use ultrasonic blades because vibration reduces sticking on gummy textures and produces smoother cuts. Once wedges are cut, they often undergo a short conditioning stage. This allows cut faces to dry slightly so the pieces do not stick together. Conditioning also equalizes moisture after cutting because freshly exposed interiors release water more quickly. Controlled air prevents surface tack that would ruin the later sugar sanding. Sour balance is built in two places. Some of it is inside the gel through acid dosing. The sharp initial sour that many watermelon slices deliver often comes from the surface. Surface sour is applied by a sanding mix that combines fine sugar with acids, like citric and malic. The blend particle size is controlled so it clings evenly and dissolves at the intended speed. If particles are too fine, they cake. If too coarse, they fall off during conveying. To make sanding adhere, the candy surface needs controlled tack. The surface cannot be wet because the sugar will dissolve and form patches. It cannot be too dry because the sugar will not bond. Many lines use a very light mist of water or syrup to create temporary tack. The mist is extremely fine, so it wets only the outermost surface. Immediately after misting, the wedges enter a sanding drum, where the sugar acid blend is dosed and distributed by tumbling. Tumbling intensity is tuned to protect edges. Wedges have pointed tips and thin green rims that can chip. Drum speed and fill level are chosen to encourage rolling rather than sliding. Rolling spreads, sanding evenly across the faces and edges. After sanding, excess sugar is screened off and collected. A short drying tunnel follows. So, the tack layer sets and the sugar crystals lock onto the surface. Apples become a uniform retail product inside a packing facility by being stabilized, cleaned, sorted, graded, waxed, and packed under tight control of temperature, moisture, and impact. The process starts when bulk filled bins of apples enter a receiving line that is designed to keep bruising low. The bins are tipped by a hydraulic dumper into a water flume or a dry cushion infeed. A flume is often used because water supports the fruit and reduces drop impact. Flow rate is set so apples separate and do not pile up. If a dry infeed is used, soft belts and low drop chutes spread the fruit into a single moving layer. From the infeed, the apples pass through a pre-rinse stage that removes loose dust and leaf fragments. Spray bars deliver water at controlled pressure, so surface debris lifts without forcing water into the stem cavity. The rinse water is filtered continuously because suspended grit can scratch skins. The fruit then moves into a washer where rotating brushes scrub the surface. Brush stiffness is chosen by variety because thin-skinned apples mark more easily. Brush speed is tuned so the fruit rotates and contacts brushes evenly instead of sliding. After brushing, the apples pass under high-volume rinses that flush away loosened residues. Drain belts and air knives remove excess surface water. Drying matters because downstream optical cameras need a stable surface reflectance. Drying also matters because wax application behaves differently on wet skins. The line often uses warm air tunnels to bring the surface to a consistent dryness without heating the fruit core. Before deep sorting, the line removes obvious non-conforming fruit mechanically. A sizing roll section can separate very small fruit that will be routed to other packs. A singulation belt then spreads apples into a consistent spacing. Singulation is one of the most important steps because all later measurement systems assume each apple is isolated. Belt speeds and lane dividers maintain spacing as fruit enters the inspection zone. Optical inspection is the central grading step. Multi-angle cameras capture images of each apple as it rotates on rollers. Lighting is controlled to reveal color, gloss, and surface defects. Algorithms measure diameter, shape, blush coverage, and background color. They also detect bruises, punctures, russeting, scab, hail marks, and stem cavity damage. Some lines add near-infrared sensing to estimate internal defects or maturity indicators. The result is a decision for every apple that determines its pack grade and its destination lane. At the same time that cameras inspect surface quality, the system measures size and weight. Size is derived from image geometry and from mechanical calipers in some designs. Weight is measured by in-motion scales that momentarily support the apple and record load. Size and weight are combined because many pack specs are defined as count per carton. Count targets require tight weight distribution, so the packed box stays within tolerance while keeping visual uniformity. Once each apple has a grade and size assignment, the line uses diverters to route it to the correct channel. Diverters can be air jets or flap gates or servo paddles. Timing accuracy is critical because fruit is moving continuously. Each apple's position is tracked from the cameras to the diverter, so the correct gate fires at the correct moment. Mistiming causes cross-grade contamination and forces rework. Many packing lines apply wax after washing and before final packing. Wax is not just cosmetic. It reduces moisture loss and stabilizes gloss. Wax is applied as a fine mist or a roll coat while apples rotate. The wax formula is chosen to form a thin continuous film without streaking. Application rate is controlled because heavy wax can look cloudy and can trap dust. After wax application, the fruit passes through a drying tunnel. Warm airflow sets the film and fixes shine. If stickers are applied, they are placed after waxing and after the surface is dry. A label head peels the sticker and presses it onto the fruit with controlled force. Placement is consistent, so labels do not wrinkle over lenticels or curve edges. The label system is synchronized to fruit spacing, so every selected apple receives one label and the label stays aligned. At this point, the line can split into two main product routes. One route is whole fruit packing. The other route is further processing into fresh cut slices or value packs. For whole fruit packing, the apples enter a packing accumulator that buffers flow. From there, they feed into either tray packing or loose fill systems. Tray packing uses molded fiber or plastic trays that hold each apple in a pocket. Tray selection is based on size count. A tray denester places an empty tray on a conveyor. Apples are then placed into pockets by synchronized drop lanes or robotic pick heads. Pocket depth and spacing reduce movement in the carton and protect skins from rubbing. Loose fill packing is used for bags or bulk cartons. In this route, apples drop into a bag former or into a carton with controlled drop height. Chutes are lined and curved to minimize impact. For bagging, a weighing system portions a target mass. Apples are released into a plastic bag and the bag is sealed. Bag seal timing is coordinated with the drop, so no fruit is caught in the seal. For bulk cartons, the system fills in layers to avoid tall drops. A leveling gate can settle apples into a stable arrangement. Carton formation is integrated into the packing line. Flat blanks are erected into cartons by a case erector. Trays or loose apples are loaded into the carton. A top pad can be placed to reduce scuffing. The carton is then closed and taped or glued. Coding prints a lot identifier and pack information. Check weighers can verify carton weight against expected range. Vision checks can confirm proper closure. A critical part of apple production is storage management inside controlled conditions. Many apples are held in cold storage before packing. Cold storage slows respiration and maintains firmness. Temperature is held near a set point and humidity is controlled to limit dehydration. Many systems use controlled atmosphere storage where oxygen is reduced and carbon dioxide is managed. This slows metabolic activity and preserves texture. Before packing, fruit is often tempered to a target temperature, so condensation does not form on skins when the fruit hits warmer air. Tempering also stabilizes wax behavior and camera performance. When the product route is fresh cut apples, the process changes after washing and sorting. Only fruit that meets internal quality targets is selected because cutting amplifies defects. Selected apples enter a coring and slicing system. The apple is centered by a cup and then pushed onto a corer. The corer removes the core and seeds in one stroke. Slicing blades then cut the apple into wedges or rings. Blade sharpness is tightly maintained because dull blades crush tissue and accelerate browning. The slicing system is designed to keep cut surfaces clean and consistent thickness. Fresh cut apples require anti-browning control. Immediately after slicing the pieces, enter a dip or spray treatment that slows enzymatic browning. The treatment is metered and contact time is controlled. Excess solution is removed by drainage and gentle air. The slices are then portioned into packs. Portioning can be done by weight or by piece count. Packs are sealed with films that control moisture and gas exchange. Some packs use modified atmosphere to slow oxidation. Sealed packs are chilled quickly to stabilize texture. Whether whole or sliced, the final steps focus on protecting quality through handling. Conveyors are designed with soft transfers. Drop heights are minimized. Accumulation tables prevent jams that would compress fruit. Packaging materials are chosen to resist moisture transfer and to maintain structure in cold environments. Cases are palletized in stable patterns that allow airflow during cold chain storage. Mangoes become a consistent retail product inside a packing facility by being stabilized, cleaned, heat-treated when required, graded by size and maturity, cooled, waxed, and packed under tight control of temperature and impact. The process begins with bulk field bins or crates entering a receiving line designed to limit bruising. Mangoes are tipped by a hydraulic dumper into a water flume or onto cushioned belts. A flume supports the fruit and reduces drop energy. Water flow is adjusted so mangoes separate and do not stack. If a dry dump is used, the system relies on soft curtains and stepped chutes to spread fruit into a single moving layer. From in feed, the fruit passes through a pre-rinse stage that removes dust and sap residues loosened during harvest and transport. Spray bars deliver water at controlled pressure so the skin is cleaned without forcing water into lenticels. The rinse stream is filtered continuously because grit in recirculated water can scratch skins. Mangoes then enter a washer where rotating brushes scrub the surface. Brush stiffness is selected by variety because skin sensitivity varies. Roller speed is tuned so each fruit rotates and contacts brushes evenly. A key mango-specific step is sap management. Mango latex can mark skins and cause dark streaks. The wash sequence is configured to remove sap films early. Water temperature and contact time are controlled to lift residues without softening the skin. After brushing, high-volume rinses flush away loosened residues. Drain belts and air knives remove surface water, so downstream, sensors see a consistent surface reflectance. Many mango lines include a hot water treatment step when required by export specifications or when a heat treatment is used to stabilize quality. The treatment uses a temperature-controlled water bath with precise residence time. Mangoes enter baskets or carriers that submerge them uniformly. Water temperature is monitored continuously because small deviations change treatment effectiveness and can also stress the fruit. Residence time is controlled by conveyor speed or basket dwell. After treatment, mangoes exit and move immediately to cooling. Cooling is staged to remove heat without creating surface condensation. A first cooling step can use a water rinse at controlled temperature. A second step uses forced air cooling tunnels to bring fruit to a target core temperature. Airflow is designed to reach all sides without creating localized cold spots. Temperature equalization matters because uneven cooling can create localized ripening differences. After washing and any treatment, the fruit enters singulation. Singulation spreads mangoes so each piece can be inspected and measured individually. Lane dividers and timing belts create consistent spacing. Proper spacing is required for accurate imaging and for correct diverter timing. Mangoes then move into an inspection zone where lighting and camera angles are controlled. Optical grading is used to classify mangoes by size, color, shape, and surface defects. Cameras capture multiple views as mangoes roll over rollers. Lighting is configured to reveal bruises, scuffs, sap burn marks, blemishes, and sunspots. Algorithms measure size and estimate volume. Some systems use near-infrared sensing to estimate internal maturity indicators such as dry matter or internal defects. The purpose is to route fruit into ripeness programs and pack grades. Weight grading can be added with in-motion scales. Each mango passes over a support that records weight. Weight data is combined with size data to assign a count class for cartons. Consistent count class is important because cartons are sold by count and expected to look uniform. The system routes mangoes into lanes that correspond to target count and grade. Maturity management is a central control point for mango packing. Mangoes continue ripening after harvest. The facility often receives fruit at different maturity levels. Sorting can separate greener fruit for longer distribution from more coloured fruit for near-term delivery. When maturity sensors are used, the system can build lots with consistent dry matter and colour stage. This reduces mixed ripeness in a single carton. Once each mango is assigned a destination lane, diverters route the fruit. Diverters can be servo gates or drop belts that release fruit into the correct lane. Timing is precise because mangoes are moving continuously. Impact control at diversion points is critical because mangoes bruise easily. Chutes are lined and curved. Drops are kept low. Accumulators are used to prevent pile-ups. After grading many lines, apply a wax or coating. The coating reduces moisture loss and improves appearance. Wax is applied as a fine mist while fruit rotates. Application rate is controlled because heavy wax can create streaks and trap dust. After waxing, mangoes pass through drying tunnels where warm air sets the film. Drying air is controlled so it sets wax without warming the fruit excessively. If stickers are required, they are applied after wax and after the surface is dry. A labeling head places a sticker at a consistent position. Placement force is controlled so the sticker adheres without tearing the skin. Label application is synchronized with fruit spacing, so no fruit is missed and no double labels occur. Packing begins with staging fruit into packing buffers. Buffers equalize flow and allow packers to fill cartons at steady speed. Mango packing often uses trays or single-layer cartons to reduce bruising. Tray packing uses molded inserts with pockets. Pocket size is matched to mango size class. Fruit is placed into pockets by synchronized lanes or by pick systems. Pocket orientation is controlled, so stem ends are positioned consistently when required by presentation standards. For loose fill or bulk cartons, the line uses gentle filling chutes. Mangoes are layered rather than dropped in a deep pile. Layering reduces pressure on lower fruit. Pads or liners can be placed between layers. The objective is to prevent pressure points that become bruises. For bag formats, mangoes are weighed into target weights and dropped into bags with controlled drop height. Bags are sealed and then packed into cases. Carton erection and closing are integrated into the line. Flat blanks are erected into cartons by a case erector. Trays or loose fruit are loaded. The carton is closed and taped or glued. Codes are printed to identify lot and pack date. Check weighers confirm cartons are within tolerance. Vision systems can confirm closure integrity. Cold chain control continues after packing. Mangoes are moved into cold rooms set to a target temperature that slows ripening without causing chilling injury. Temperature set points depend on variety and maturity stage. Airflow in. Storage is designed to cool cartons evenly. Humidity is controlled to reduce dehydration while preventing condensation. Carton vents align to allow airflow through the stack. Some supply chains use controlled atmosphere storage or transport. Oxygen and carbon dioxide levels can be adjusted to slow metabolism. Gas control must be stable because excessive carbon dioxide can cause off flavor and internal injury. Even without controlled atmosphere, the core control is maintaining stable temperature through storage and transport. If the facility also produces fresh cut mango, the process branches after grading. Only fruit meeting internal quality targets is selected. Mangoes are peeled using mechanical peelers or knife systems that remove skin with minimal flesh loss. Flesh is sliced from the seed with guided blades. The slices are cut into cubes or strips with calibrated cutters. Cut size is controlled because it affects drainage and pack appearance. Cut pieces are chilled quickly to slow softening. They are portioned into packs by weight and sealed. Packaging films are selected to manage moisture and oxygen exchange. Fresh strawberries arrive in bulk containers and are immediately transferred onto vibrating sorting tables. The surface trembles in rapid pulses, spreading the fruit into a single layer. Optical scanners sweep across the moving belt, detecting color density and surface irregularities. Jets of compressed air fire in milliseconds, ejecting underripe or bruised berries. The selected strawberries continue forward in a uniform stream. The fruit drops into a rotating drum washer. High-pressure sprays strike from multiple angles, stripping away soil and field residue. The drum slowly turns, ensuring every surface is exposed to the water jets. Excess water drains through perforations while the berries advance toward the discharge chute. A final mist rinse removes remaining particles before the fruit exits onto a dewatering conveyor lined with absorbent rollers. Next, the strawberries pass beneath stainless steel blades that remove stems with precise vertical cuts. The trimmed berries fall into a stainless hopper, feeding an industrial crusher. Inside the crusher, rotating paddles press the fruit against a perforated screen. The flesh collapses into a thick pulp, releasing juice and seeds. The sound shifts from a soft tumble to a wet grinding hum as the texture transforms into a uniform mash. The pulp moves into a heated processing tank equipped with a slow-turning agitator. Granulated sugar is metered in through a screw feeder. The agitator sweeps through the mixture, dissolving sugar crystals into the strawberry mass. Gentle heat intensifies the aroma while evaporating excess moisture. The mixture thickens slightly as soluble solids increase. A refractometer probe continuously measures sugar concentration, adjusting feed rates to reach precise sweetness. Once balanced, the strawberry blend flows through a fine mesh filter. Seeds and fibrous fragments are separated, producing a smooth puree. The filtered puree enters a vacuum deaerator where trapped air bubbles rise and collapse under reduced pressure. The surface briefly foams, then settles into a glossy, uniform liquid. This step prevents oxidation and preserves the bright red hue. Parallel to fruit preparation, the dairy base begins in large insulated tanks. Fresh cream and whole milk are pumped in controlled proportions through stainless pipelines. Load cells beneath the tanks monitor weight to ensure exact ratios. Liquid sugar syrup joins the blend through automated valves, eliminating undissolved crystals. The mixture swirls under high-speed agitators, forming a homogeneous liquid. Milk solids and stabilizers are introduced through a powder induction system. Fine. Powders are drawn into the vortex created by the spinning mixer, preventing clumping. The stabilizers hydrate gradually, thickening the base and improving body. The sound of the mixer deepens as viscosity increases. Temperature sensors regulate the mixture to maintain optimal hydration conditions. The blended dairy base is pumped into a plate heat exchanger for pasteurization. Thin layers of liquid flow between heated stainless plates. Hot water circulates on the opposite side, raising the temperature rapidly. The mixture reaches pasteurization temperature within seconds and is held briefly in a holding tube. This precise thermal treatment eliminates unwanted microorganisms while preserving flavor integrity. Immediately after heating, the mixture travels back through the heat exchanger, where chilled water cools it down quickly. The rapid drop in temperature prevents overcooking. The base exits at a cold, controlled temperature and flows into aging tanks. Inside these tanks, slow, paddles rotate gently, preventing separation while allowing fat molecules and proteins to stabilize. Over several hours, the mixture thickens slightly as fat crystallizes and stabilizers fully hydrate. Once aged, the dairy base is directed toward a high-pressure homogenizer. The liquid is forced through microscopic openings under intense pressure. Fat globules shatter into tiny droplets, dispersing evenly throughout the mixture. the texture becomes smoother and more stable. The transformation is audible as a sharp hiss accompanies the sudden pressure release. The homogenized base and the prepared strawberry puree converge in a blending tank. Automated flow meters synchronize their entry to achieve the desired fruit concentration. As they merge, rotating blades fold the red puree into the pale dairy liquid. The color shifts from off-white to a uniform pink. The mixture thickens slightly as fruit solids integrate with the cream structure. The combined mixture flows into a continuous ice cream freezer. Inside the cylindrical freezing barrel, refrigerant circulates around the outer shell, drawing heat away rapidly. A dasher spins within the barrel, scraping frozen layers from the inner wall. The scraping action prevents large ice crystals from forming. Simultaneously, controlled air is injected into the mixture. Tiny air bubbles disperse evenly, increasing volume and creating a light texture. As the mixture churns, it transforms from liquid to semi-solid. The texture resembles soft snow. Temperature probes monitor the freezing point continuously. The dasher blades slice through the thickening mass with rhythmic precision, producing a steady mechanical hum. Within minutes, the ice cream reaches a soft serve consistency and is extruded from the barrel through a nozzle. For varieties containing strawberry pieces, an inclusion feeder introduces diced fruit at this stage. The small cubes drop into the flowing stream and are folded gently by a low-speed auger. The movement distributes the pieces evenly without crushing them. Bright fragments remain suspended in the creamy matrix. The semi-frozen ice cream moves through insulated pipes into filling machines. Containers travel along a conveyor beneath multi-nozzle fillers. Each nozzle descends and releases a measured volume. The soft ice cream spirals into the container, forming layered folds. Vibrating plates beneath the conveyor remove trapped air pockets and level the surface. Lids are placed automatically by a rotary placer. A brief downward press seals each container. Date codes are printed in precise black ink on the lid surface. The filled units advance into a hardening tunnel. Inside, powerful fans blast air at extremely low temperatures. The air circulates at high velocity, stripping remaining heat from the product. During hardening, ice crystals stabilize into a fine structure. The temperature at the core drops steadily until the entire mass becomes firm. The transformation locks in the overrun and prevents structural collapse. The containers exit the tunnel solid and rigid. They pass through a metal detection system that scans each unit for metallic fragments. A reject arm removes any container that fails the scan. Approved units continue to a cartoning station where multiple containers are grouped and wrapped in printed sleeves. Mechanical arms fold cardboard around the stack with crisp, angular movements. The cartons move onto a palletizing line. Robotic arms lift entire layers and stack them with geometric precision. Each layer aligns perfectly, forming a stable cube. Stretch film wraps tightly around the stacked load, binding it into a single secure mass. Before storage, samples from each batch are tested in a texture analyzer. A probe presses into the frozen ice cream, measuring resistance and consistency. The data confirms proper freezing and air incorporation. Color sensors verify uniform pink tones, ensuring the strawberry dispersion is consistent. Throughout the entire process, stainless steel pipelines connect every stage. Pumps pulse rhythmically, maintaining continuous flow. Valves open and close in timed sequences controlled by automated systems. Digital panels display temperatures, pressures, and flow rates in real time. Each transformation occurs in a precise order, from raw fruit and liquid dairy to aerated frozen structure. The final packaged strawberry ice cream rests in cold storage at stable sub-zero temperatures. Inside each sealed container, microscopic ice crystals, evenly distributed air cells, stabilized fat droplets, dissolved sugars, and concentrated strawberry solids form a balanced matrix. The journey from whole berries and fresh cream to smooth frozen dessert is defined entirely by controlled motion, measured heat exchange, rapid freezing, and exact mechanical coordination. Raw milk is delivered to the processing facility in insulated stainless steel tanks. Upon arrival, the milk is passed through a series of mesh strainers to remove any large particulate matter. It then flows into a balance tank, where load cells continuously measure the volume and ensure accurate downstream processing. The temperature of the milk is monitored by inline thermocouples, confirming it is within a range suitable for further processing. The milk proceeds to a clarification step. High-speed centrifuges spin at thousands of revolutions per minute, using centrifugal force to separate any remaining somatic cells, small debris, or micro-impurities. Clarified milk exits the centrifuge through a continuous discharge system, maintaining a smooth, consistent flow. The removal of these particles ensures uniformity in subsequent heating and fermentation stages. Next, the milk enters a standardization phase. Skim and cream fractions, measured precisely by flow meters, are blended to achieve the desired fat content for Greek yogurt. The mixture passes through automated mixers that homogenize the dairy liquid, dispersing fat droplets uniformly to prevent separation and ensure a smooth, final texture. Homogenization is critical for creating a thick, creamy mouthfeel after fermentation and straining. The standardized milk then undergoes pasteurization. It flows through a plate heat exchanger where thin layers of milk pass between heated stainless steel plates. Hot water or steam circulates on the opposite side, rapidly raising the temperature to a controlled level, typically around 85 to 90 degrees Celsius. The milk is held at this temperature in a holding tube for several seconds to destroy pathogenic bacteria and deactivate enzymes. Pasteurization ensures safety and stabilizes proteins for improved coagulation. Immediately after pasteurization, the milk is cooled rapidly via the same heat exchanger in counterflow, using chilled water or glycol to bring it down to the fermentation temperature, typically around 42 to 45 degrees Celsius. Rapid cooling prevents overcooking the proteins and preserves a neutral flavor profile, readying the milk for bacterial culture inoculation. The milk then flows into fermentation tanks. Starter cultures containing specific strains of Lactobacillus bulgaricus and Streptococcus thermophilus are introduced in measured doses. Automated dosing systems ensure exact quantities of active cultures are dispersed evenly. The milk is gently agitated to distribute the bacteria uniformly without creating excessive air bubbles, which could interfere with texture development. Fermentation begins as the tank is held at controlled temperature. Heating jackets or circulating water jackets maintain constant warmth. The bacteria metabolize lactose into lactic acid, gradually lowering the pH of the milk. As acidity increases, casein proteins destabilize and aggregate, forming a gel network. The process is monitored via inline pH sensors, which track the decrease in pH toward the target range, typically between 4.5 and 4.6. During fermentation, slow, intermittent stirring ensures uniform heat distribution and prevents a dense skin from forming on the surface. The gel forms gradually, transforming the liquid milk into a soft, viscous curd. The curd's elasticity is assessed through viscometers or occasional manual sampling to determine the readiness for straining. After the curd reaches the desired acidity and consistency, fermentation ceases by cooling. The tanks are chilled using recirculated cold water or brine jackets, rapidly bringing the yogurt to around 4 degrees Celsius. Cooling halts bacterial activity, stabilizes the gel network, and prevents over-acidification. The cooled yogurt now has a creamy, spoonable texture, but is still high in whey content compared to traditional Greek yogurt. The next stage is straining, which is critical to producing Greek yogurt's characteristic thickness. The yogurt is pumped into centrifugal separators or stainless steel sieves equipped with fine mesh filters. Mechanical pressure or centrifugal force separates liquid whey from the solid curd. In some systems, vacuum-assisted filtration accelerates whey removal while maintaining the integrity of the protein matrix. The result is a dense, creamy yogurt with concentrated milk solids. For large-scale production, the strained yogurt may pass through multiple sequential centrifuges or filters to achieve the target consistency. Each stage incrementally removes whey, reducing moisture content and increasing protein concentration. The sound of liquid passing through perforated plates and the gentle hum of centrifugal rotors indicate continuous separation. Monitoring instruments track moisture levels and protein content to ensure consistency batch to batch. After straining, the thickened yogurt may be blended briefly to homogenize texture. Low shear paddle mixers fold the curd gently, eliminating pockets of firmer or looser gel while avoiding aeration that could introduce unwanted air bubbles. The texture at this point is dense but smooth, with a uniform pale white color. If flavoring or fruit inclusions are desired, they are introduced in a separate blending stage. Natural fruit purees, syrups, or flavor extracts are metered into the thick yogurt using precision dosing pumps. Rotating augers fold these additives gently, maintaining the yogurt's viscosity while achieving even distribution. Inline mixing sensors ensure consistent blending without breaking the gel network. The yogurt then moves to filling equipment. Containers travel along conveyors beneath precision nozzles that deposit exact volumes. The yogurt flows in a continuous stream or spirals into the containers, forming a smooth surface. Vibrating platforms may gently level the yogurt and remove trapped air bubbles, preventing voids that could affect shelf appearance and texture. Filled containers pass through automated capping systems. Lids are sealed with controlled pressure, ensuring airtight closure. Date coding machines print batch information directly on the lid surface. The sealed units are then conveyed into cold storage chambers. Rapid cooling continues as the yogurt is brought down to storage temperature, typically around 0 to 4 degrees Celsius. This step further stabilizes texture, slows bacterial activity to preserve shelf life, and maintains product integrity during handling. Temperature-controlled conveyors and chill tunnels ensure minimal fluctuation, maintaining the thick, creamy structure of the Greek yogurt. Throughout the production line, stainless steel pipelines connect tanks, filters, and filling machines. Pumps regulate flow rate, while automated valves open and close in precise sequences. Sensors continuously monitor flow, temperature, pH, and protein content, providing real-time data to the control system. Any deviation triggers adjustments to maintain consistent product quality. During quality control, samples are drawn from various points along the line. Rheometers measure viscosity, ensuring the yogurt meets textural specifications. Moisture analyzers confirm the whey content aligns with Greek yogurt standards. Colorimeters check for uniformity in hue and brightness. Microbiological tests verify that bacterial counts are within acceptable ranges, confirming proper fermentation and pasteurization effectiveness. The final product exhibits a dense, creamy texture with minimal whey separation. Protein concentration is high, a result of controlled straining and careful homogenization. The yogurt retains a subtle tang from lactic acid development and, if included, uniform fruit dispersion or flavor infusion. Containers are stacked and wrapped for storage, ready to maintain their structure until distribution. Robotic palletizers lift layers of containers and stack them with precise alignment. Stretch film wraps the pallet, securing it for cold transport. Throughout handling, the Greek yogurt remains chilled, preventing separation or texture degradation. Each pallet holds hundreds of containers, reflecting the cumulative precision of pasteurization, fermentation, straining, blending, and packaging. Every stage of the process emphasizes mechanical control and precision. From raw milk clarification through homogenization, controlled fermentation, whey removal, and final packaging, the production relies on continuous monitoring of temperature, pH, viscosity, and moisture. The interplay of mechanical devices, centrifuges, mixers, heat exchangers, pumps, and filling machines ensures consistency, texture, and protein concentration in every batch. The journey from liquid milk to thick, creamy Greek yogurt is defined by sequential transformations: purification, fat standardization, heat-induced protein denaturation, bacterial fermentation, gel formation, controlled cooling, whey separation, and gentle blending. Each transformation is quantified and monitored, producing a stable, high-protein yogurt with characteristic density and smoothness. Even at microscopic scale, the structure is precise. Fat. Droplets are homogenized and dispersed. Protein networks form consistent matrices, and tiny air pockets are minimized. Whey removal concentrates solids without fracturing the gel. The final yogurt exhibits uniform texture, flavor, and acidity due entirely to controlled mechanical and thermal processes. Mascarpone cheese arrives in insulated tanks and is first examined for temperature and consistency. The cheese is pumped through stainless steel pipelines into a blending vat. High shear agitators rotate within the vat, dispersing the dense cheese uniformly and ensuring no lumps remain. The mixers are equipped with variable speed motors, allowing precise control of shear forces to maintain the creamy texture without aerating excessively. Load cells beneath the vat monitor the mass of cheese entering the mixer to confirm exact quantities for recipe consistency. Egg yolks are separated mechanically using rotary egg breaking machines. The eggs are cracked, and yolks and whites are divided using centrifugal separators. Yolks are collected in stainless steel hoppers and gently pumped to pre-blending tanks. Inline viscometers monitor the viscosity of the yolk stream, ensuring smooth, homogeneous flow before incorporation. Sugar is introduced via screw feeders, passing through heated hoppers to prevent clumping. Paddle agitators fold the sugar into the yolks gradually, allowing partial dissolution and formation of a light, smooth custard base. The mascarpone is folded into the yolk-sugar mixture using low-speed planetary mixers. Rotating arms sweep through the mixture, gently folding the dense cheese into the custard without incorporating air. Sensors track torque on the mixer shafts, providing data on viscosity progression. Once fully integrated, the mixture has a uniform, glossy appearance and a controlled thickness that will later allow it to layer effectively in the final dessert. Separately, espresso coffee is brewed continuously. Water is pumped into high-pressure stainless steel extraction units at precisely 92 to 95 degrees Celsius. Ground coffee is metered into portafilters or drum roasters, compacted by mechanical tampers. Pressurized water flows through the grounds at a controlled rate, extracting soluble solids and aromatic compounds efficiently. The resulting espresso flows into holding tanks equipped with heat jackets to maintain temperature until required for soaking. A continuous conveyor system moves the espresso from brewing to the soaking station with minimal exposure to air, preserving flavor integrity. Optional liqueurs, such as coffee-flavored or almond-based spirits, are stored in temperature-controlled tanks. Flow meters regulate the addition of liqueur to the espresso in mixing tanks. Static mixers create a homogeneous coffee liqueur blend, maintaining precise flavor ratios. The mixture passes through inline thermometers, ensuring it is at a temperature that will saturate the ladyfinger biscuits without prematurely softening them. Ladyfinger biscuits are produced separately. Flour, sugar, eggs, and leavening agents are combined in a high-speed mixing ribbon or planetary mixer. The batter's viscosity is monitored by inline rheometers to ensure it is thick yet pourable. Once mixed, the batter is extruded through nozzle systems onto conveyor belts in uniform finger shapes. The fingers pass through tunnel ovens with controlled zones of convection and infrared heating, baking them to a firm yet spongy consistency. Cooling conveyors allow the biscuits to reach ambient temperature while retaining flexibility for soaking. The cooled ladyfingers are transferred to an automated soaking line. Conveyors align the biscuits in single layers beneath nozzles that dispense measured volumes of coffee liqueur mixture. The liquid jets impact the biscuit surface precisely, soaking the exterior without disintegration. Vibrating trays under the nozzles gently shake the biscuits, promoting uniform absorption. Sensors track moisture content in real time, adjusting nozzle flow rates and conveyor speed to achieve consistent saturation across all units. After soaking, the biscuits are deposited into filling trays by robotic arms or gravity-fed systems. The trays are designed with cavities corresponding to the final product size. Each cavity receives a layer of soaked ladyfingers, forming the base layer of the tiramisu. Sensors confirm correct placement, detecting misaligned or broken biscuits, which are automatically removed from the line. The mascarpone yolk sugar mixture is then transferred to depositing machines. Multi-nozzle filling heads extrude precise amounts over the biscuit base. Linear actuators and programmable logic controllers coordinate nozzle motion to spread the mixture evenly. Low-speed paddles may be used after deposition to smooth the layer without incorporating air, preserving the dense, creamy texture characteristic of tiramisu. If multiple layers are required, the process repeats. Another layer of soaked ladyfingers is added atop the mascarpone layer, followed by additional cheese mixture deposition. Robotic arms and precision conveyors ensure exact alignment of layers, avoiding displacement or uneven thickness. Inline laser sensors monitor height and uniformity across the tray, signaling adjustments in deposition volumes to maintain consistency batch to batch. Cocoa powder application occurs once all layers are complete. Fine mesh sifters deliver a controlled dusting of cocoa over the surface. Pneumatic shakers or vibrating plates assist in evenly distributing the powder, preventing clumping or excessive coverage. In large-scale production, automated dispensing heads move across the tray to maintain a uniform layer of cocoa, forming the characteristic top finish of the tiramisu. Color sensors verify the evenness and intensity of the cocoa layer. Completed trays proceed to refrigeration tunnels. Cold air circulates at high velocity, rapidly bringing the product down to approximately 4 degrees Celsius. The cooling process is gradual enough to preserve the gel structure of the mascarpone layer, but fast enough to stabilize moisture in the ladyfingers. Fans and airflow deflectors maintain uniform temperatures across trays, preventing condensation or uneven chilling. During storage and transport, trays remain in temperature-controlled environments. Sensors monitor core temperatures to ensure the mascarpone mixture remains firm without freezing. Refrigerated conveyors maintain orientation and prevent tilting, which could disrupt layered structure. Shock-absorbing supports minimize vibrations, preserving the integrity of delicate layers during handling. Before packaging, automated vision systems inspect each tray. Cameras detect layer uniformity, surface smoothness, and cocoa distribution. Deviations beyond preset tolerances trigger removal or correction of the tray. This ensures that the visual appearance aligns with specifications. Weight sensors confirm that each tray contains the correct mass of ingredients, compensating for minor variations in deposition or biscuit absorption. Once inspection is complete, trays move to sealing stations. Transparent film or lids are applied using mechanical arms with pneumatic actuators. Vacuum or controlled atmosphere sealing may be applied in some systems to extend shelf stability without altering texture. Labeling machines print batch codes, production dates, and other required data on lids or shrink sleeves, using high-resolution thermal printers synchronized with conveyor motion. Finished and packaged tiramisu trays are then conveyed to palletizing robots. Each layer of trays is stacked systematically, maintaining geometric stability. Stretch film is applied in tight spirals around the stack to secure pallets for refrigerated storage. Temperature and humidity sensors within the storage area ensure that the dessert maintains optimal conditions until distribution. Refrigerated transport. Systems continue this temperature-controlled environment, preserving texture, flavor, and visual quality. Throughout production, stainless steel pipelines connect each step: cheese preparation, egg blending, coffee brewing, biscuit soaking, layering, and packaging. Pumps regulate flow, while automated valves control timing and volume precisely. Temperature probes, viscosity meters, pH sensors, and weight scales provide real-time data to the central control system, allowing fine adjustments in process parameters without manual intervention. Each transformation, from raw cheese and eggs to layered cocoa top dessert, relies on precise mechanical and thermal control. Optional flavor modifications, such as chocolate shavings or alternative liqueur blends, are introduced at designated stages using metered dispensers. High-speed augers fold additives into the mascarpone mixture without breaking the gel, ensuring uniform distribution. When applied to the surface, sprinkling systems position toppings precisely without disturbing the layers below. Quality assurance tests occur at multiple stages. Rheometers evaluate the spreadability and firmness of the mascarpone mixture. Moisture analyzers verify that ladyfingers retain enough liquid to be soft but not soggy. Refractometers measure sugar concentration in both the custard and coffee liqueur blend. Visual inspection ensures color consistency, and spot microbiological sampling confirms the effectiveness of pasteurization and safe storage. The final product exhibits precise physical properties: a dense yet creamy mascarpone layer with stable gel structure, a sponge layer of ladyfingers soaked to optimal moisture content, and a fine cocoa powder surface finish. The internal protein and fat matrix supports the structure while retaining a soft, spoonable texture. Each spoonful reflects careful coordination of ingredient ratios, temperature, shear forces, and layer integration. Even at a microscopic level, the structural integrity is controlled. Proteins in the mascarpone form a cohesive network, trapping air minimally. Fat droplets are distributed evenly, and moisture from coffee infusion is absorbed uniformly in the sponge layer. Cocoa particles adhere lightly to the top without penetration, ensuring visual consistency and flavor profile. The industrial strawberry layer cake manufacturing sequence begins at the bulk dry storage terminal. Large-scale suction blowers move sifted pastry flour into the primary weight hoppers. These hoppers utilize load cells to ensure a precision of within 100 grams. A secondary pneumatic line introduces powdered glucose into the flour stream. The glucose prevents the starch from retrograding during the freezing process. Sodium bicarbonate is injected at a ratio of 2 kilograms per metric ton of flour. This leavening agent reacts with acidic components to create the crumb structure. A Z horizontal ribbon blender rotates to achieve a 99% homogeneity rating. The hydration phase starts inside a twin-screw continuous mixing unit. Liquid whole eggs are metered into the chamber at a constant flow rate. These eggs are chilled to 5 degrees Celsius to prevent protein denaturation. A high-pressure pump injects vegetable oil through a series of micro nozzles. The oil coats the flour particles to inhibit excessive gluten development. Deionized water is added to reach a specific gravity of 1.05 for the batter. a jacketed cooling system keeps the mixing chamber at a steady 18 degrees Celsius. This temperature control is vital for the stability of the chemical leavening agents. The aeration stage uses a high shear rotostator head to incorporate nitrogen gas. Nitrogen provides a finer bubble structure than standard atmospheric air. The resulting batter density is measured by an inline densitometer. This device sends real-time feedback to the gas flow controller. A batter density of 0.45 grams per cubic centimeter is the target for this recipe. The batter travels through stainless steel piping to the manifold depositor. This manifold spans the width of a 1 meter wide steel conveyor belt. Individual piston pumps discharge 60 milliliters of batter into silicone-coated molds. The molds move into a direct gas-fired tunnel oven with 12 independent heat zones. Zone 1 operates at 140 degrees Celsius to facilitate initial lift. The belt speed is calibrated to ensure a 20-minute residence time. Moisture sensors at the midpoint monitor the humidity levels of the oven atmosphere. High humidity prevents the formation of a thick crust on the sponge surface. Zone 6 reaches a peak temperature of 190 degrees Celsius. This heat triggers the caramelization of surface sugars for color development. The final zones gradually reduce the temperature to set the internal cake matrix. Automatic vacuum depanners lift the baked sponges from the molds at the oven exit. The sponges are placed onto a modular plastic cooling belt. This belt travels through a HEPA-filtered cooling tunnel for 30 minutes. Ambient air is pulled through the sponges to remove internal heat. The core temperature must reach 22 degrees Celsius before the slicing phase. A battery of reciprocating serrated blades cuts the sponges into 3 equal layers. The blade height is adjusted by microservos based on laser thickness measurements. Each layer is diverted to a separate conveyor for specific ingredient application. The strawberry coulis production wing operates as a closed-loop thermal system. Frozen strawberry blocks are pulverized by a high-torque industrial crusher. The resulting slurry moves into a vacuum evaporator to concentrate the natural sugars. Evaporation occurs at 60 degrees Celsius to preserve the volatile flavor compounds. Liquid pectin is injected into the concentrate to establish a thermo-reversible gel. The pH is adjusted to 3.2 using a concentrated lemon juice buffer. This acidity is necessary for the pectin to form a stable molecular network. The coulis is then passed through a fine mesh filter to remove seeds. A plate heat exchanger cools the coulis to 8 degrees Celsius for immediate use. The first applicator station uses a waterfall distributor to coat the base layer. A weight check scale verifies that 40 grams of coulis are applied to each cake. The second sponge layer is placed on top by a high-speed vacuum pick-and-place unit. A second applicator deposits a layer of strawberry-infused cream over the middle sponge. This cream contains stabilized dairy fats and emulsified strawberry solids. The third sponge layer completes the vertical stack before the primary icing phase. The outer frosting is prepared in a pressurized aeration tank for maximum volume. Anhydrous milk fat is blended with sugar syrup and natural stabilizers. The mixture is whipped at 500 revolutions per minute under 3 bars of pressure. This process creates a stable foam with a shelf life of 12 days. The frosting is pumped to a dual-axis robotic icing station. The cake rotates on a pedestal while a side scraper applies the frosting. A top spreader levels the frosting to a thickness of 4 millimeters. Optical cameras inspect the coverage for any gaps or uneven patches. Decorative strawberry rosettes are formed by a multi-nozzle extrusion head. This head uses a star-shaped aperture to create the traditional fluted texture. The extrusion pressure is synchronized with the conveyor belt speed. A secondary station applies a fine mist of pectin glaze over the frosting. This glaze prevents the frosting from drying out during storage. Fresh strawberry quarters are placed into the rosettes by a vision-guided robotic arm. These strawberries are pre-treated with an ascorbic acid wash to prevent browning. A final dusting of pulverized dextrose is applied for visual contrast. The cakes enter a spiral blast freezer for rapid stabilization. Liquid carbon dioxide is sprayed into the chamber to reach -40 degrees Celsius. This rapid cooling creates small ice crystals to preserve the cake texture. The cakes spend 45 minutes inside the spiral freezer. An automated pusher arm moves the frozen cakes toward the packaging line. Cardboard flats are folded into boxes by a mechanical mandrel system. A plastic liner is inserted into each box to prevent moisture loss. The cakes are lowered into the boxes by a soft grip robotic hand. A metal detector scans every boxed cake for potential physical contaminants. This unit can detect ferrous particles as small as 0.5 millimeters. Any rejected boxes are diverted to a secondary inspection bin. A weight grader ensures the final product meets the 500-gram specification. The boxes are sealed with a tamper-evident adhesive strip. An inkjet coder prints the batch number and the production timestamp. The boxes are stacked into corrugated shipping cases by a robotic palletizer. These cases are then wrapped in polyethylene film for structural stability. The palletized goods are moved into the high bay cold storage warehouse. This facility uses an automated storage and retrieval system for inventory management. The temperature is maintained at -18 degrees Celsius with zero fluctuation. Loading docks are equipped with thermal seals to prevent heat ingress during shipping. Every delivery truck is monitored via GPS for real-time temperature tracking. This data is logged into the Quality Assurance Database for compliance. The entire production line can output 800 cakes per hour. This efficiency is achieved through the total integration of mechanical and digital controls. The cleaning in place system cycles through the entire piping network every shift. Hot caustic solution removes fat deposits from the mixing and pumping units. A secondary acid wash neutralizes any mineral scale in the heating elements. The final rinse uses sterilized water to ensure a zero residue environment. All wastewater is treated in an on-site filtration plant before discharge. This plant recovers 90% of the water for non-food industrial use. The factory operates on a 24-hour cycle to maximize equipment utilization. This rigorous process ensures the consistency of the industrial strawberry layer cake. The air quality in the assembly room is monitored for microbial counts. Surface swabs are taken from the conveyor belts every 4 hours. These samples are incubated in the laboratory to check for yeast and mold. The flour silos are equipped with explosion venting panels for safety. Dust collection systems pull fine particles away from the mixing stations. The grease used in the mechanical bearings is food grade certified. All electrical panels are NEMA rated for protection against high pressure washdowns. The facility utilizes LED lighting to reduce heat generation in the cooling zones. The vegetable oil is stored in nitrogen-blanketed tanks to prevent oxidation. These tanks are equipped with ultrasonic level sensors for inventory tracking. The sugar syrup is kept in heated vats to prevent crystallization. All raw ingredients are barcoded upon entry for full traceability. This allows the factory to track a single cake back to the specific wheat harvest. The conveyor motors utilize variable frequency drives for precise speed control. These drives reduce energy consumption during periods of lower production. The central control room monitors every motor and sensor in the building. The robotic arms are programmed using a proprietary motion control language. These programs allow for rapid changeovers between different cake sizes. The ultrasonic blades are sharpened using a specialized grinding unit every weekend. This maintenance ensures the cleanest possible cut for the sponge layers. The silicone molds are inspected for surface degradation after every 1,000 cycles. Worn molds are recycled to prevent any silicone migration into the batter. The packaging cardboard is sourced from sustainably managed forests. This commitment to materials ensures the long-term viability of the production model. The industrial fabrication of brownies begins with the high-volume intake of raw commodities. Bulk storage silos hold up to 50 tons of specialized pastry flour. This flour features a low protein content to ensure a tender crumb. Pneumatic transport lines move the flour into the primary sifting station. Vibratory screens remove any particles larger than 200 microns. Cocoa powder arrives in hermetically sealed containers to prevent moisture absorption. This cocoa is typically alkalized to reach a pH level of 7. The alkalization process darkens the powder and mellows the flavor profile. Automatic scales measure the cocoa with an accuracy of 10 grams. A separate line delivers granulated sucrose from a central hopper. The sugar is pulverized into a fine mesh to facilitate rapid melting. Liquid fats are stored in stainless steel vats with internal heating coils. These coils maintain the fat at a constant 45 degrees Celsius. This temperature prevents the lipid chains from crystallizing in the pipes. Refined soybean oil provides the necessary moisture for a fudgy texture. Some formulations utilize anhydrous milk fat for a richer mouthfeel. The primary mixing phase utilizes a high-torque industrial blender. The liquid fats enter the mixing chamber through pressurized nozzles. Cocoa powder is added next to create a thick chocolate paste. This stage is known as the wet rub in the baking industry. The friction from the blades raises the paste temperature slightly. Infrared sensors monitor this heat to prevent scorching of the cocoa. A secondary mixer prepares the hydration base for the batter. Liquid eggs are pumped from refrigerated tanks at 4 degrees Celsius. These eggs undergo inline pasteurization before they reach the blender. A plate heat exchanger flashes the eggs to 60 degrees Celsius. They are immediately cooled back to 10 degrees Celsius. This process eliminates pathogens without coagulating the egg proteins. Natural humectants, like vegetable glycerin, are added to the egg mix. Glycerin binds water molecules to the starch during the baking cycle. This chemical bond prevents the brownie from becoming stale. The dry ingredients meet the wet base in a continuous mixer. The flour is folded in by a twin screw agitation system. This system prevents the overdevelopment of gluten in the wheat. Excessive gluten would make the brownie tough and bread-like. Salt is injected into the stream at a precise 0.2% ratio. It acts as a flavor enhancer for the chocolate components. A small amount of sodium bicarbonate provides a chemical lift. This leavening agent reacts with the acidic cocoa particles. The batter moves through a series of refining rollers. These rollers reduce the particle size of the sugar and cocoa. A final particle size of 30 microns ensures a smooth mouthfeel. The refined batter is pumped into a vacuum de-aeration tank. This tank removes any trapped air bubbles from the mixing stage. Removing air increases the density of the final brownie slab. A dense structure is required for the fudge classification of the product. The batter reaches a final viscosity of 15,000 centipoise. Industrial brownies often feature inclusions like semi-sweet chocolate chips. These chips are stored in a climate-controlled room at 18 degrees Celsius. This prevents the chips from blooming or sticking together. A vibratory feeder dispenses the chips into the moving batter line. A static mixer folds the inclusions in without shearing them. The ratio of inclusions is usually 10% of total weight. The batter is now ready for the depositing stage. A high-speed manifold spans the width of the production conveyor. This manifold contains 24 individual piston-driven nozzles. The nozzles deposit the batter into large steel baking trays. These trays are coated with a permanent Teflon layer. An automated sprayer applies a secondary film of vegetable oil. The oil ensures a clean release after the cooling phase. Each tray receives exactly 12 kilograms of brownie batter. Optical sensors verify the weight and level of every tray. A mechanical oscillating plate spreads the batter to the corners. This ensures the brownie slab has a uniform thickness of 30 millimeters. The trays enter a multi-zone convection tunnel oven. The oven is 60 meters long to accommodate high-speed production. It is heated by a series of natural gas burners. The first zone is set to 150 degrees Celsius. This initial heat initiates the melting of the sugars. The second zone increases the temperature to 170 degrees Celsius. This is the primary, baking phase where the structure sets. Convection fans circulate the air at 5 meters per second. This constant airflow ensures the edges do not burn before the center. Steam injection ports maintain a 40% humidity level. The humidity prevents the top surface from cracking or crusting. The final oven zone facilitates the Maillard reaction. This chemical reaction occurs between the sugars and amino acids. It creates the complex flavor profile associated with baked chocolate. The total residence time in the oven is 28 minutes. An automated arm extracts the hot trays at the oven exit. The trays move onto a modular plastic cooling belt. This belt travels through a spiral cooling tower. Filtered air at 15 degrees Celsius blows across the trays. The cooling process must be gradual to prevent the slab from shrinking. The internal temperature must drop to 25 degrees Celsius. This cooling phase typically lasts for 45 minutes. A vacuum depanner lifts the entire brownie slab from the tray. The slab is placed onto a high-density polyethylene cutting board. This board moves toward the ultrasonic slicing station. Ultrasonic blades vibrate at 20,000 Hz per second. This vibration prevents the dense brownie from sticking to the knife. The blades make vertical and horizontal cuts simultaneously. This creates perfectly square units with sharp edges. The standard size is 5 centimeters by 5 centimeters. Any trim from the edges is diverted to a rework bin. This trim is ground up for use in other chocolate products. The individual brownie units are separated by a divergent conveyor. This conveyor increases the space between the brownies for packaging. Some brownies pass through an enrobing station for a chocolate coating. The enrober pours a curtain of tempered chocolate over the units. A blower clears the excess chocolate to maintain a thin layer. The coated brownies enter a secondary cooling tunnel. This tunnel sets the chocolate coating to a high gloss finish. The brownies move into the primary packaging zone. A robotic arm picks up 4 brownies at a time. It places them into a pre-formed plastic blister tray. The tray provides structural support during shipping and handling. A flow wrap machine encapsulates the tray in a polymer film. This film is treated with a nitrogen flush. Nitrogen replaces the oxygen to prevent the oxidation of fats. This gas flushing technique doubles the product's shelf life. The film is heat sealed at both ends by a rotating jaw. A laser printer applies the lot number and expiration date. The individual packs move toward the secondary packaging station. A case packer assembles 24 packs into a corrugated box. This box is sealed with a pressure-sensitive adhesive tape. A check weigher verifies that the case meets the target weight. Any underweight cases are automatically pushed off the line. A palletizing robot stacks the cases onto a wooden pallet. The robot follows a specific pattern to ensure stack stability. A stretch wrap machine secures the load with several layers of plastic. The pallet is tagged with a radio frequency identification label. This label contains the entire production history of that batch. The pallets are moved to a temperature-controlled warehouse. This warehouse is kept at 18 degrees Celsius. Quality control technicians perform a moisture analysis on every batch. They use a halogen moisture analyzer to check for consistency. The target moisture content for a fudge brownie is 12%. A texture analyzer measures the force required to compress the brownie. This ensures the chewiness meets the brand specifications. The cocoa solids are verified using a spectrophotometer. This device measures the light absorbance of the chocolate. The production line operates on a 24-hour schedule. A clean-in-place system sanitizes the mixes between batches. This system uses hot water and biodegradable and detergents. All water used in the plant undergoes reverse osmosis filtration. The factory utilizes a closed-loop energy recovery system. Heat from the ovens is captured to preheat the incoming air. This reduces the carbon footprint of the manufacturing facility. The flour silos are equipped with explosion suppression systems. Fine flour dust can be highly combustible in large volumes. Spark detectors monitor the pneumatic lines for any heat buildup. The packaging room is kept at a positive air pressure. This prevents any dust or insects from entering the clean zone. Workers wear specialized lint-free suits and head coverings. All tools are made from detectable stainless steel. The vegetable oil tanks are nitrogen blanketed to prevent rancidity. Oxygen is the primary enemy of long-term fat stability. The supply chain is tracked using a digital ledger system. Every ingredient can be traced back to its original farm. This level of transparency is standard for industrial food. Production. The brownie recipe is stored in a secure digital vault. The central computer controls every motor and valve in the plant. The automated manufacturing of cheesecake begins with the large-scale processing of the base crust material. Bulk quantities of graham flour and wheat flour are combined in a high-speed industrial shredder. This unit pulverizes the baked biscuits into a uniform crumb with a diameter of 2 millimeters. The crumbs are moved via a vibratory conveyor to a horizontal blending drum. Molten butter is injected into the drum through a series of atomizing nozzles. The butter acts as a binding agent to ensure the crust remains structurally sound. Granulated sugar is added to the mixture to facilitate caramelization during the baking stage. The crust mixture is transferred to the primary molding line by a vacuum lift system. Circular spring-form pans move along a specialized belt at a rate of 40 units per minute. A volumetric depositor drops exactly 100 grams of the crumb mixture into each pan. A pneumatic tamping head descends to compress the crumbs with 50 pounds of pressure. This compression creates a dense and level foundation for the cheese filling. The sides of the pans are simultaneously brushed with a light film of release agent. This prevents the cake from adhering to the metal during the cooling phase. The preparation of the cheese filling occurs in a separate, climate-controlled mixing terminal. Industrial-sized blocks of cream cheese are loaded into a vertical, high-shear mixer. These blocks are tempered to exactly 20 degrees Celsius to ensure maximum pliability. A heavy-duty agitation arm breaks the cheese down into a smooth and aerated paste. Liquid sour cream is introduced through a flow-controlled piping network. The sour cream provides the necessary acidity to balance the richness of the fats. Large quantities of liquid whole eggs are then metered into the mixing chamber. These eggs act as the primary emulsifier and structural setting agent for the batter. Pure vanilla extract is injected into the stream via a micro-dosing pump. The mixing speed is reduced to avoid the over-incorporation of atmospheric air. Excess air in the batter causes the cheesecake to crack during the thermal expansion phase. The batter is monitored by an inline viscometer to ensure it reaches 4,000 centipoise. A final stage of the mixing process involves the addition of cornstarch. The starch binds to the free moisture to prevent the occurrence of syneresis. The finished batter is pumped through insulated stainless steel lines to the depositing station. A multi-piston manifold accurately dispenses the batter over the prepared crust. Each pan is filled to 90% of its total volume to allow for expansion. The pans are then transferred into a continuous water bath tunnel oven. This oven utilizes a shallow pool of circulating water to regulate the heat transfer. The water bath ensures the temperature never exceeds 100 degrees Celsius at the base. This thermal regulation prevents the edges of the cake from cooking faster than the center. The oven is divided into 4 distinct thermal zones for precise moisture control. Zone 1 maintains a high humidity level of 80% to prevent surface drying. The temperature in this initial stage is set to 120 degrees Celsius. Zone 2 increases the heat to 140 degrees Celsius to set the egg proteins. The moisture levels are gradually reduced in Zone 3 to facilitate color development. A light golden hue is achieved on the surface through controlled convection airflows. The final zone utilizes a cooling gradient to stabilize the cake before it exits the oven. The total residence time within the tunnel oven is approximately 90 minutes. An automated arm removes the pans from the water bath at the end of the line. The cakes enter a primary cooling chamber to reduce the internal temperature to 40 degrees Celsius. This slow cooling prevents the cheesecake from pulling away from the sides of the pan too quickly. The pans move into a blast chiller where the temperature is dropped to 4 degrees Celsius. This rapid cooling stage is essential for the final set of the dairy fats. The cheesecake must reach a firm consistency before the depanning process begins. A mechanical depanner uses a series of gentle suction cups to lift the cake from the mold. The springform rings are automatically expanded and retracted for sterilization. The cakes are placed onto a sanitized plastic transport disc for the finishing stage. Many industrial cheesecakes receive a fruit-based topping at this point in the sequence. A secondary manifold applies a layer of fruit puree or glaze to the top surface. The glaze is heated to 60 degrees Celsius to ensure a smooth and glass-like finish. It is immediately cooled by a localized cold air jet to lock the topping in place. If the recipe requires a swirl pattern, a robotic needle system is utilized. The needles inject colored fruit syrups into the wet batter before the baking stage. The robotic arm follows a pre-programmed geometric path to ensure visual consistency. For decorative borders, a multi-nozzle whipping station applies cream cheese frosting. The frosting is extruded through fluted tips to create a traditional rosette pattern. The cakes then move to the high-frequency ultrasonic slicing station. The ultrasonic blades vibrate at 30,000 Hz to prevent the cheese from sticking. This technology allows for perfectly clean cuts through the dense and sticky filling. The machine can slice the cheesecake into 12 or 16 equal wedges. Each wedge is separated by a thin piece of parchment paper to prevent re-adhesion. The parchment paper is fed from a continuous roll and cut by the same blade. The sliced cakes are moved to the primary packaging terminal by a synchronized conveyor. The packaging process involves placing the cake into a rigid plastic dome. This dome protects the decorative frosting and the delicate top glaze. A cardboard base provides structural support and contains the product information. The packages are moved into a vacuum sealing machine to remove excess oxygen. An inert gas flush is sometimes used to maintain the freshness of the dairy components. The sealed units are then placed into individual retail boxes by a pick-and-place robot. These boxes are constructed from high-grade recycled paperboard with a moisture barrier. A laser printer applies the batch code and the specific expiration date to each box. The boxes are grouped into master cases for bulk distribution to wholesalers. Each master case is tracked by a unique radio frequency identification tag. The cases are stacked on pallets by a heavy-duty robotic palletizing arm. The pallets are wrapped in multiple layers of clear stretch film for stability. The finished product is stored in a deep freeze warehouse at -20 degrees Celsius. This freezing stage allows for long distance transport without compromising the texture. The quality control department monitors the fat content of every batch using a centrifuge. The moisture to solids ratio is checked using a rapid thermal analyzer. Any batch that falls outside of the 5% variance range is rejected. The pH level of the batter is measured to ensure the sour cream has reacted correctly. A texture analyzer probes the center of a sample cake to measure the resistance. This ensures the mouthfeel is consistent across every single production run. The color of the top glaze is verified using a digital spectrophotometer. The industrial facility uses a centralized control system to manage the ingredient flow. Silos are equipped with ultrasonic level sensors to trigger automatic reordering. The water used in the process undergoes a 3-stage purification sequence. This includes carbon filtration and ultraviolet sterilization to ensure purity. The air in the assembly room is filtered through a series of HEPA units. These filters remove nearly all airborne contaminants from the production environment. The floors are sloped to integrated drainage systems for easy cleaning. Every 4 hours, the entire line undergoes a localized sanitation cycle. High-pressure steam is used to clean the depositor nozzles and mixing blades. The conveyor belts are constructed from antimicrobial blue polyurethane material. This material resists the growth of bacteria and is easy to inspect visually. The factory operates on a 24-hour schedule with 3 shifts of workers. The output can reach several thousand units per hour depending on the cake size. This massive scale is necessary to meet the global demand for frozen desserts. The supply of cream cheese is delivered via refrigerated tanker trucks. These tankers are emptied into the holding vats using a pressurized air system. The butter is stored in a separate heated room to maintain a liquid state. All dry ingredients are passed through a metal detector before entering the mixer. This ensures that no foreign objects from the harvesting process remain in the flour. The packaging materials are stored in a dry zone to prevent mold growth. The logistics team coordinates the departure of refrigerated trucks every 6 hours. Oreo wafer rolls are produced using a dual-stream manufacturing process involving continuous wafer sheet production and separate cream filling preparation, which are later synchronized through an automated integration line. The raw materials for the wafer component are dosed automatically from bulk silos into individual weighing hoppers. The base formulation consists of low-protein wheat flour, high-fat alkalized cocoa powder, refined sucrose, leavening agents, salt, water, and a controlled amount of oil-based emulsifiers. Dry ingredients are metered into a high-capacity horizontal mixer with dual-axis paddles designed for uniform blending. Liquids are injected through precision nozzles mounted at the top of the mixing chamber. The total mixing cycle is programmed between 6 and 8 minutes at varying RPMs, first for dry distribution, then for incorporation of wet components. Dough temperature is maintained between 22 and 26 degrees Celsius. Moisture content is monitored via inline near-infrared sensors and must fall within 10.0 to 11.5% before release to the forming line. Dough is transferred via a covered screw conveyor to a pre-sheeting station. Here, a primary roller flattens the dough into a rough sheet approximately 5 mm thick, which then feeds into a 3-stage reduction system. Each stage includes a pair of high-precision, counter-rotating steel rollers with micrometric gap control that sequentially reduce the dough thickness to 1.2 pounds. Dough tension is maintained using differential speed rollers to avoid tearing. Edges are trimmed continuously using rotary cutters, and trimmings are conveyed pneumatically back to the pre-mix hopper for reintegration. The thin dough sheet enters a continuous baking tunnel consisting of 8 to 12 independently controlled zones. Heating is achieved via direct gas-fired convection and radiant ceramic panels. Internal zone temperatures range from 180 to 220 degrees Celsius depending on the position. Air velocity, humidity, and conveyor speed are continuously adjusted via PID feedback loops. Total bake time is between 85 and 105 seconds. Baked sheets are discharged onto a mesh cooling belt, where ambient forced air coolers reduce sheet temperature to below 30 degrees Celsius within 90 seconds. Cooling is followed by longitudinal slitting. Circular slitting blades mounted on adjustable shafts divide the wide wafer sheet into narrow, uniform ribbons matching the final roll width. Slitting accuracy is maintained using laser alignment sensors. Each ribbon is immediately guided into a spiral roll-forming station equipped with a rotating mandrel. A servo-controlled drum pulls the ribbon over the mandrel, while controlled tension and heat reactivation of the dough surface allows the strip to roll into a rigid, cylindrical shell. Formed rolls are passed through a stabilization tunnel maintained at 65-75 degrees Celsius with low humidity to fully set their shape. Rolls are discharged onto a buffer conveyor which feeds into the cream filling station. In parallel, the cream filling is prepared from sugar, hydrogenated vegetable oil, milk solids, lecithin, artificial flavor, and small amounts of stabilizers. Ingredients are batch loaded into a jacketed mixing vessel with shear blades rotating at 1400 and 1600 RPM. Oil is added slowly to prevent separation, and the entire mixture is heated to 45-48 degrees Celsius. Mixing continues for 10 to 15 minutes until a homogeneous emulsion is achieved. The finished cream is transferred through insulated stainless steel pipes to pressurized holding tanks. Agitators maintain cream fluidity and prevent phase separation. The filling is then pumped to multiple servo-driven depositors aligned with each lane of the wafer roll conveyor. Each nozzle delivers a calibrated cream column into the core of each roll, with filling weights accurate to plus 0.2 grams. The nozzle retracts dynamically during deposit to ensure central cream alignment and full core penetration. Cream-filled rolls pass through a secondary cooling tunnel set to 10 degrees Celsius for 60 seconds to solidify the filling. Thermal imaging sensors confirm internal stabilization before exiting. At this stage, each roll is individually scanned for dimensional conformity, surface defects, and fill anomalies. Rolls not meeting target criteria for weight, symmetry, or visible cream containment are diverted via pneumatic actuators into separate waste chutes. Approved rolls proceed to flow wrapping. Individual rolls are aligned using vibratory feeders and grouped into packaging sets based on SKU configuration. Film is dispensed from reels and formed into tubes by collaring mechanisms. Horizontal seal jaws apply pressure and heat at 135-145 degrees Celsius for 0.3 to 0.5 seconds to close the ends and seal the longitudinal seam. Nitrogen gas is flushed into the package before sealing to displace oxygen and slow fat oxidation. Each wrapper is printed with batch code, timestamp, and best before date using thermal inkjet printers synchronized with the machine cycle. Wrapped products are conveyed to a cartoning unit, where robotic arms pick and place the flow-wrapped units into pre-formed cartons. Cartons are constructed from pre-creased flat blanks that are folded and glued using hot melt adhesive. Carton fill conformation is performed using weight sensors and machine vision. Completed cartons are sealed, labeled, and aggregated into corrugated shipper boxes. Each shipper box is barcoded for traceability and palletized in accordance with standard load configurations. Palletized loads are stretch-wrapped and transferred to climate-controlled warehouse storage. Storage areas maintain relative humidity below 60% and ambient temperature between 18 and 22 degrees Celsius to prevent wafer degradation and cream migration. Inventory turnover is managed via FIFO principles enforced by warehouse management software, which integrates with factory MES and ERP systems for batch tracking. Process validation occurs every production shift. Operators test dough rheology, sheet thickness, baking curve, moisture content, cream viscosity, deposit weight, roll hardness, and package seal integrity. Data is recorded in the batch record along with any machine adjustments or anomalies. All critical control points, including cream deposit temperature, bake time, and packaging seal strength, are electronically logged and must fall within specification limits or trigger corrective action. Cleaning in place procedures are scheduled every 8 to 12 hours. Cream lines are flushed with heated water, followed by alkaline detergent, acid rinse, and sterile water rinse. Wafer production lines use dry cleaning methods for rollers and belts, followed by compressed air cleaning and manual wipe down of forming mandrels. Swab testing is used to verify microbial cleanliness, and ATP bioluminescence testing is used to assess organic residue. Production yield is calculated by comparing in-feed material weight to packaged product weight, adjusted for expected waste. All off-spec rolls, excess cream, and packaging rejects are weighed and categorized into waste type. Cream residue is routed into closed collection tanks for food waste processing, while wafer rejects are disposed of according to facility-specific food waste handling protocols. All mechanical systems, mixers, sheeters, formers, depositors, and sealers are maintained under a scheduled preventive maintenance program. Bearings, blades, nozzles, and conveyors are inspected and replaced based on run hours. PLC logic controllers monitor machine health via vibration sensors, motor load curves, and cycle time deviation analysis. Batch documentation includes raw material lot numbers, machine settings, environmental conditions, operator identification, in-process test results, and any deviations from standard operating conditions. These records are archived digitally and are subject to internal audits, third-party verification, and regulatory inspection. Full traceability is retained for every unit produced. Nutella B-Ready consists of 3 major components manufactured on synchronized but separate production lines: a wafer shell, a Nutella filling, and the final packaging. Each component is produced under tightly controlled parameters using fully automated equipment integrated into a high-throughput, continuous processing line. The outer shell is made from a low-moisture, wheat-based dough formulated to bake into a crisp, blister-free wafer. The dough formulation begins with dosing refined wheat flour, sugar, salt, leavening agents, and a blend of plant-based fats into an enclosed paddle mixer. Dry ingredients are dispensed from silo systems into individual weigh hoppers with accuracy to within plus 0.1%. Liquids, including water and emulsifiers, are metered from heated tanks using flow meters. The mixer operates at multiple speeds for uniform hydration and structural development. Once the dough reaches the required consistency, typically between 22% and 25% moisture content, it is discharged via bottom gate valves into an auger conveyor leading to the forming line. The dough passes through a series of lamination rollers where it is flattened to a precise thickness of 1.0-1.4 millimeters. Differential speed control across rollers prevents tearing and ensures uniform surface tension. Edge trimmings are continuously recycled to minimize waste and maintain dimensional consistency. The laminated sheet enters a rotary molding system. This consists of a rotating die roller with cavity molds shaped to match the profile of the Nutella B-Ready shell. The dough is pressed into the molds using counter-rotating pressure rollers. An adjustable doctor blade removes excess dough from the roller surface. Molded wafers are transferred via a vacuum pickup system to a baking mesh conveyor, which passes through a tunnel oven with multiple independently controlled zones. The oven zones maintain specific temperature gradients between 180 degrees and 220 degrees, optimized for water evaporation, structural hardening, and color development. Each zone's airflow is modulated by variable frequency drive fans to control browning without burning. Baking duration is typically between 80 and 110 seconds. Thermocouples and moisture sensors measure real-time parameters. Upon exiting, wafers are cooled in line using ambient air-blown axial fans, reducing temperature to under 30 degrees Celsius within 2 minutes. Simultaneously, Nutella filling is prepared in a separate processing room using a continuous mixing system. Ingredients including refined sugar, vegetable oil, skimmed milk powder, cocoa, and hazelnut paste are dosed using mass flow meters and pneumatic transfer lines. Mixing occurs in a double-jacketed emulsification vessel with counter-rotating impellers operating at 800 to 1200 RPM. The temperature is held between 40 degrees and 45 degrees C during mixing to maintain fluidity and preserve emulsion stability. The finished Nutella filling is pumped through heat-insulated stainless steel piping into buffer tanks connected to multi-head depositor units. These depositors are aligned with the conveyor lanes carrying the pre-formed wafer shells. Each depositor nozzle dispenses a precise amount of filling, usually between 12 and 16 grams, into the hollow cavity of each wafer. Fill weight is monitored using inline load sensors that reject any units outside the tolerance band of plus 0.3 grams. To prevent air entrapment during deposition, the filling nozzle retracts during injection at a synchronized rate, matching the filling viscosity and back pressure. Cream flow is assisted by low-pressure nitrogen to maintain a consistent stream and eliminate pulsing. After filling, each shell passes through a cooling tunnel maintained at 10 to 12 degrees to solidify the fat phase of the filling and prevent oil migration into the wafer wall. Following cooling, a pre-molded wafer lid is applied to seal each filled shell. These lids are formed from the same dough and are baked separately on a synchronized rotary system. A robotic arm equipped with vacuum suction cups picks and places each lid onto the open cavity. An edible adhesive compound, typically a glucose-based syrup, is applied to the perimeter edge to create a bond. Pressure rollers compress the lid and base together for mechanical adhesion. After sealing, each unit passes through a mechanical inspection station. High-speed cameras and laser profilometers verify shell integrity, alignment, lid placement, and overall dimensions. Any product with cracks, offset seals, or excessive height deviation is automatically rejected via pneumatic diverter arms. Approved units move into the packaging preparation line. Packaging begins with flow wrapping. Individual Nutella B-Ready units are spaced on timing belts and fed into the wrapping machine using servo motor controlled pushers. Wrapping film is fed from a roll and formed around each unit via a forming collar. Horizontal and vertical seals are applied using heated sealing jaws that operate at 130 degrees, 145 degrees Celsius. Modified atmosphere packaging is implemented via nitrogen gas injection prior to sealing to displace oxygen and extend shelf life. Each flow-wrapped unit is scanned by barcode readers and printed with date codes and traceability numbers using thermal inkjet printers. Units are counted and grouped into sets of 6 or more, depending on market configuration. Grouping is performed using star wheel collators, which align the units into rows for secondary packaging. Secondary packaging uses flat fold cartons erected via vacuum cup pick-and-place systems. Hot melt glue is applied via nozzles to predefined folding flaps, which are pressed closed by mechanical arms. Each carton receives printed labels containing product name, nutritional data, batch code, allergen information, and certification marks. Cartons are weighed for content verification and stacked into larger corrugated shipping boxes using layer-forming robotic packers. Palletizing is performed by 6-axis robotic arms with end effectors designed to grip multiple boxes per cycle. Standard Euro or industrial pallets are loaded based on customer logistics requirements. Pallet patterns are configured to ensure structural stability and airflow clearance. Once loaded, pallets are wrapped using stretch film machines that apply 250% pre-stretched film to secure load integrity during transit. Each pallet is tagged with a pallet license plate containing full production metadata, including line number, production date, shift code, storage conditions, and destination route. Pallets are moved into finished goods, storage warehouses with temperature and humidity control systems set to maintain between 18 degrees Celsius and 20 degrees, with relative humidity under 60%. Pallet positions are recorded using warehouse management systems with RFID scanners and barcode tracking. Throughout the production process, all inputs, outputs, and in-process conditions are monitored by a centralized SCADA system. Parameters such as oven temperature, mixer torque, depositor cycle counts, wrapping seal integrity, and product rejection rates are logged and archived. Alerts are generated automatically for any deviation outside programmed thresholds. Operators access these systems via HMI touchscreens placed at each station. Sanitation protocols are applied on a rotating schedule. Dough preparation lines are cleaned with dry brushing, followed by ethanol-based surface wipes. Cream handling equipment undergoes full CIP cycles involving alkaline wash, acid rinse, and sterile water flush, validated with conductivity and pH sensors. Wrapping and cartoning stations are cleaned with compressed air, brush downs, and isopropyl surface sanitizers. Swab samples are taken post-cleaning and tested for microbial load. Preventive maintenance is performed weekly on all forming dies, depositor heads, conveyor bearings, and sealing modules. Wear components are replaced based on run-hour tracking. Calibration is conducted daily on dosing equipment, weighing scales, and thermocouples. All calibration records are maintained in compliance with regulatory documentation standards. Product testing occurs hourly. Samples are collected from each production lane and evaluated for weight, length, height, filling content, shell texture, seal strength, and packaging tightness. Sensory analysis includes bite resistance, shell-to-filling ratio, and flavor consistency. Non-conforming samples trigger root cause investigations documented in deviation reports. The entire Nutella B-Ready manufacturing process is standardized to allow for duplication across multiple production facilities with identical output quality. Parameters are optimized to prevent moisture migration, mechanical breakage, and oil separation, which are common defects in filled wafer-based snack formats. Final product shelf life is tested under accelerated and ambient conditions to verify packaging efficacy. Chips Ahoy. Cookie manufacturing begins with bulk ingredient handling systems that store raw materials in separate silos or intermediate bins under controlled conditions. Low moisture, fine milled wheat flour is pneumatically conveyed from outdoor silos into batch weigh hoppers located above the main mixing area. Granulated sugar, brown sugar, cocoa solids, salt, and baking soda are stored in indoor silos or gravity-fed bins and fed into weigh stations using screw feeders with plus 0.1% dosing precision. Vegetable shortening and liquid invert sugar are stored in stainless steel jacketed tanks with continuous recirculation to prevent phase separation. The shortening is heated to maintain fluidity at 45 to 50 degrees Celsius, and the invert sugar is pumped at a constant rate through positive displacement pumps. All liquid and dry ingredients are tracked using an integrated batching control system that verifies real-time mass flow and batch integrity using load cells and flow meters. Each batch is loaded into a planetary batch mixer with a dual paddle agitator system. Mixing follows a 3-stage, time-controlled sequence. First, creaming of shortening and sugars is performed for 3 to 4 minutes at low speed. Next, flour and leavening agents are incorporated at medium speed for an additional 3 minutes. Finally, the mixture is scraped down and mixed on high speed for 1 to 2 minutes until a homogeneous dough with uniform texture and target moisture content of 18 to 20% is achieved. Temperature sensors monitor the dough throughout mixing to ensure it remains within the 20 to 24 degrees Celsius range. Overheating is prevented by jacketed cooling systems circulating chilled glycol solution. Once the dough is fully mixed, it is discharged into a stainless steel hopper that feeds a cookie depositor via auger conveyors. Before entering the depositor, chocolate chips are metered into the dough using volumetric feeders to achieve a distribution ratio of approximately 20% by weight. The cookie depositor uses servo-controlled pistons to extrude uniform dough portions directly onto a continuously moving Teflon-coated oven band. Deposit weight per cookie is calibrated to between 18 and 21 grams, depending on SKU. Deposited dough pieces are spaced using optical sensors to maintain consistent center-to-center distance and allow for uniform spread during baking. Each dough piece is flattened slightly by a roller to control shape retention. The baking oven is a hybrid convection and radiant tunnel oven with multiple independently controlled heating zones. Total bake time is typically between 8 and 11 minutes. The oven band runs at a set speed that is continuously adjusted by a PID controller based on real-time surface temperature and humidity readings. Oven zone temperatures range from 160 degrees Celsius in early zones to up to 210 degrees Celsius in final zones to ensure progressive starch gelatinization, moisture evaporation, Maillard reaction, and fat migration. Cookies are monitored during baking using infrared pyrometers that measure surface temperature. Steam injection systems in early oven zones are optionally used to control surface moisture and prevent excessive cracking. Exhaust fans in later zones remove excess humidity and volatile compounds. By the time cookies exit the oven, internal moisture content is reduced to between 3 and 5%, ensuring shelf-stable texture and microbial safety. Upon exiting the oven, cookies are transferred onto a wire mesh cooling conveyor system. Ambient air is directed from below and above the belt using axial fans to achieve uniform cooling to under 30 degrees Celsius in less than 3 minutes. Sensors at the end of the cooling belt check surface temperature before transferring cookies to the inspection area. Conveyor vibrations are minimized to prevent cookie breakage during transfer. Each cookie passes under a vision inspection system equipped with high-resolution cameras and infrared lighting. Software algorithms evaluate cookie shape, surface cracking, chip dispersion, color uniformity, and diameter tolerance. Any cookies failing to meet visual standards are rejected using high-speed air jets. All rejected cookies are weighed, logged, and diverted to waste bins for offline handling. Approved cookies move to the packaging station via a system of vibratory conveyors that align and group the cookies into required configurations. For multi-pack packaging, cookies are grouped into stacks using rotary collators and staged for wrapping. Individual flow packs are created using horizontal form-fill-seal machines. Film is pulled from rolls, shaped around each cookie group, and sealed using heated crimp jaws operating at 130 to 150 degrees Celsius. Modified atmosphere packaging may be used with nitrogen flushing to reduce oxygen and delay lipid oxidation. Each wrapped package receives a printed date code, batch code, and line identification number using thermal inkjet printers synchronized with the conveyor belt. Packages are weighed on inline check weighers with rejection arms for any unit falling outside of mass tolerances. Wrapped units are inserted into cartons using robotic pick-and-place arms with vacuum grippers. Cartons are sealed with hot melt glue at 165 degrees Celsius and pressed under controlled pressure to ensure full adhesion. Secondary packaging lines aggregate cartons into shipping cases. Cases are erected from flat blanks, filled automatically, and closed with either glue or tape depending on distribution requirements. Completed cases are printed with pallet codes, production timestamps, and destination routing labels. Automated guided vehicles, AGVs, or roller conveyors transfer cases to palletizers. Palletizing robots layer the cases using defined stacking patterns optimized for pallet stability and load efficiency. Each pallet is scanned for completeness using weight and barcode validation before being stretch wrapped in polyethylene film at 250% pre-stretch. Wrapped pallets are moved to finished goods warehouses with controlled temperature and humidity, typically 18 to 20 C and 50 to 60% RH. Every stage of the process is controlled and logged using a manufacturing execution system, MES. Batch records include ingredient lot numbers, mixing parameters, bake curves, oven temperatures, deposition weights, packaging counts, inspection rejections, and finished product quantities. Quality control technicians collect hourly samples to perform destructive and non-destructive testing on cookies. Tests include diameter measurement with calipers, moisture analysis via moisture, analyzer, texture profile analysis using 3-point bending rigs, and chip count per cookie via manual visual audit. Organoleptic tests include bite resistance, sweetness intensity, and flavor profiling under controlled conditions. Data is stored electronically and checked against specification ranges defined in the product specification documents. Production lines are cleaned on a rotating schedule. Between batches, dry cleaning is performed using brushes and vacuum systems to remove flour dust and crumbs. At daily intervals, equipment is disassembled and sanitized using foaming alkaline cleaners, followed by water rinses and food-safe sanitizers. Chocolate lines undergo specialized cleaning to prevent fat bloom and cross-contamination. Allergen control zones are enforced through physical separation of lines, color-coded tools, and allergen-specific cleaning validations. Swab tests for protein residues are performed on high-contact surfaces after each cleaning cycle. If any allergen residue exceeds the defined limit, cleaning is repeated and verified before production resumes. Downtime events such as depositor jams, film feed interruptions, or oven temperature deviations are tracked via the line control system. Operators record the event time, cause, and corrective actions. Line productivity is measured using overall equipment effectiveness (OEE) metrics, including availability, performance, and quality yield. Preventive maintenance on mixers, ovens, conveyors, depositors, and packaging machines is scheduled based on runtime hours. Critical components such as servo motors, bearings, seal jaws, and roller chains are monitored for vibration and thermal performance. Spare parts inventory is maintained in real time using a computerized maintenance management system, CMMS. Finished product samples are retained from each batch for shelf life testing. These samples are stored under accelerated and ambient conditions and tested at intervals for texture degradation, moisture migration, lipid oxidation, and packaging integrity. Results are used to confirm product expiration dates and to evaluate packaging material performance. All operations conform to global food safety standards such as GFSI benchmarking and are subject to internal audits and third-party certification. Traceability systems allow for immediate upstream and downstream tracking of all product components within minutes of any query. Any deviations from process controls trigger root cause analysis under a corrective and preventive action (CAPA) protocol. Dairy Queen ice cream begins with the formulation of a liquid ice cream mix that contains a specific balance of milk solids, butterfat, sweeteners, stabilizers, and emulsifiers. all designed to create a product with a soft serve texture, rich flavor, and the structural integrity to hold shape when dispensed at below freezing temperatures. The process starts with the metering of liquid ingredients into a high-capacity stainless steel mixing tank. Milk, cream, and liquid sweeteners, such as corn syrup, are pumped from refrigerated storage tanks using automated pumps that are controlled through a programmable logic controller system. The precise volumes are determined by batch recipes that are stored digitally and loaded into the mixing unit via operator interface panels. Dry ingredients like skim milk powder, dextrose, and stabilizer emulsifier blends are added through a dry powder feeder positioned over the mixing tank. As the powders are introduced, high-speed impellers and rotor-stator mixers circulate the mixture, dispersing solids uniformly and ensuring the base is homogeneous. This initial mix is agitated continuously for a set period until the solution reaches a uniform temperature and particle distribution. Once mixed, the liquid ice cream base is pumped through a series of inline filters to remove any clumps, undissolved particles, or foreign matter before proceeding to the pasteurization stage. Pasteurization is a critical thermal process that ensures microbiological safety and improves the mixer's ability to support uniform freezing and aeration. The base mix is pumped through a plate heat exchanger system, which uses hot water or steam on one side of the stainless steel plates and the ice cream mix on the other. The two fluids never touch, but heat is transferred efficiently across the metal surfaces. The mix is quickly heated to a target temperature, typically around 80 to 85 degrees Celsius, and held at that temperature for a predetermined number of seconds, usually no more than 25, before being rapidly cooled to below 4 degrees Celsius using chilled water or glycol solution in the next section of the exchanger. The rapid heating and cooling prevent unwanted protein denaturation while killing potential pathogens. The chilled, pasteurized mix is then transferred to an aging tank. These tanks are large, insulated stainless steel vessels equipped with slow-speed agitators that maintain gentle circulation without incorporating air. The mix is aged for a minimum of 4 hours, often overnight, to allow the fat crystals to partially solidify and the stabilizers and emulsifiers to fully hydrate. This aging process improves body, creaminess, and melt resistance of the final product and ensures a consistent structure when the mix is frozen later. After aging, the liquid mix is pumped into a continuous freezer. This is where the transformation from liquid to frozen soft serve occurs. The continuous freezer is a high-efficiency, jacketed stainless steel cylinder containing a rotating scraper blade assembly and a direct expansion refrigeration jacket filled with ammonia or another refrigerant. As the mix enters the chamber, it is chilled to approximately 6 to 8 degrees Celsius while being whipped rapidly by the rotating blades. This mechanical action accomplishes two things at once. It freezes the water content of the mix into fine ice crystals and incorporates air into the structure to create overrun. Overrun is the term used to describe the volume of air introduced into ice cream, expressed as a percentage of the original mix volume. Dairy Queen soft serve typically has a controlled overrun around 45%, meaning 100 liters of base mix will become 145 liters of finished product. This air is crucial for texture, mouthfeel, and lightness. It is injected through filtered nozzles as the blades churn the mixture. The balance of air and ice must be tightly regulated. Too much air leads to foaminess, while too little creates a heavy, dense product that doesn't dispense smoothly. The frozen, aerated soft serve exits the continuous freezer at a semi-solid state and is transferred immediately into sterile holding tanks or directly into distribution containers, depending on the factory design. In larger operations, the soft serve may be pumped into pre-chilled, bag-in-box containers made of multi-layered, food-safe plastic film that protects the product from light and moisture. Each bag is filled by volume through a no-drip valve, sealed mechanically, labeled with a production code and expiration date, and moved to refrigerated storage. In other systems, the soft serve may be routed into pressurized stainless steel kegs or bulk plastic drums equipped with quick connect couplings for easy installation at the retail dispenser level. These containers are filled in clean rooms under positive pressure airflow to eliminate airborne contamination. The filled containers are immediately stored at sub-zero temperatures in blast freezers or walk-in cold rooms set to maintain the product just below the freezing point without hardening the mix entirely. From here, the frozen product is shipped in refrigerated trucks to the point of sale, typically a retail location equipped with a dedicated soft-serve dispensing machine. These machines are miniaturized versions of the industrial continuous freezer used in the factory. Each machine contains a hopper that holds the soft-serve mix, an auger or scraper blade assembly, and a narrow freezing cylinder cooled by either air or water-based refrigeration systems. When the machine is activated, the product is pulled from the hopper into the freezing cylinder where it undergoes a final freezing and aeration stage. The mix is chilled further to about 9 degrees Celsius while the blades whip it to preserve consistency. When the lever on the dispenser is pulled, the pressurized frozen product is extruded through a specially designed nozzle that imparts the signature spiral swirl to the ice cream as it is dispensed into a cone or cup. Each part of this process, from raw milk to cone, relies on tightly controlled mechanical parameters, time-sensitive transitions, and a closed system design that ensures the finished Dairy Queen soft serve has a consistent texture, smooth pour, and creamy mouthfeel. The cooling cycles, flow rates, agitation speeds, syrup-to-air ratios, and thermal profiles are all digitally monitored at every stage using PLCs, sensors, thermocouples, and SCADA systems. Adjustments are automated to keep the output within strict tolerances. To ensure quality, samples are pulled at multiple points in the process for physical, chemical, and microbiological testing. These include fat content analysis using infrared spectroscopy, overrun verification using displacement methods, viscosity measurement through flow cups or rotational viscometers, and sensory testing by trained tasters who evaluate mouthfeel, melt profile, sweetness, and aftertaste. Sanitation procedures are carried out daily or between batches. All pipes, valves, hoses, and tanks in the mix production system are cleaned in place using automated CIP systems that cycle through pre-rinse, caustic wash, acid rinse, and final sanitizing steps. Soft serve dispensers at the retail level are cleaned manually with specialized brushes and food-safe detergents, followed by complete reassembly and sanitization with hot water flushes to ensure hygiene is maintained without altering the flavor of future batches. Every production batch is traceable by date, time, machine, operator, and ingredient lot, logged in a database that allows for immediate traceback in case of any quality issues. Digital records are kept for regulatory compliance and internal process optimization, helping to refine recipes, extend shelf life, and reduce variability between runs. Bluebell ice cream production begins with the assembly of the ice cream base, which is the liquid foundation used to create every flavor. This base must be smooth, homogeneous, microbially safe, and physically stable throughout the freezing, hardening, and distribution stages. To prepare it, the process starts in a mixing room where stainless steel blending tanks are used to combine raw ingredients such as whole milk, cream, skim milk powder, sugar, corn syrup solids, and stabilizers like guar gum or carrageenan. These ingredients are stored in separate bulk storage silos or tanks at controlled temperatures and are pumped into the mix tank using automated volumetric dosing systems. The control panel interfaces allow operators to select a formula code that precisely dictates the ratios required for each batch. As the ingredients are added to the tank, high shear impellers begin to mix the contents, breaking down solid particles and dispersing fats evenly into the water phase. The temperature is kept in the range of 40 to 50 degrees Celsius to aid solubility and prevent premature thickening. Once mixed into a smooth liquid, the batch is sent through a plate heat exchanger where it is heated rapidly to pasteurization temperatures, usually around 82 to 85 degrees Celsius, and held for 25 to 30 seconds to eliminate any harmful bacteria and extend shelf life. This pasteurization step is monitored using digital sensors that track the flow rate, inlet and outlet temperatures, and holding times. Immediately after pasteurization, the base is cooled just as rapidly by the second half of the heat exchanger using chilled glycol solution or water, dropping the temperature of the mix to around 4 degrees Celsius. This chilled mix is directed into insulated aging tanks where it is gently agitated and held for a minimum of 4 hours. The aging process allows the milk fat to partially crystallize, which improves body and mouthfeel, while stabilizers fully hydrate and develop viscosity. The aging tanks are jacketed and equipped with temperature controllers to ensure the mix stays cold and consistent across the entire volume. From the aging tanks, the base mix is pumped through a filtration unit and into continuous freezers. These freezers are the heart of the transformation process, where liquid mix becomes soft, semi-solid ice cream through a combination of rapid cooling and mechanical aeration. Each freezer consists of a horizontal freezing barrel that's jacketed for refrigeration and fitted with a rotating dasher blade assembly that scrapes the frozen mix from the inside wall while simultaneously blending in air. This air is filtered and injected under pressure to create overrun, the volume of air in the ice cream, which typically ranges from 60 to 90% depending on the product line. The dasher speed and airflow rate are tightly controlled to produce a uniform texture with consistent aeration. As the mix freezes, small ice crystals begin to form, stabilized by the partially solidified fat structure. The blades continue to whip the mixture while keeping the internal temperature around 5 to 7 degrees Celsius, cold enough to form a spoonable texture without fully hardening. At this stage, inclusions like chocolate chips, cookie dough, brownies, caramel swirls, or fruit pieces are introduced. These mix-ins are added using ingredient feeders synchronized with the freezer output. The feeders are auger-based or belt-driven and feed precise quantities of inclusions into the flow stream so that distribution is even but gentle, ensuring that delicate ingredients are not crushed or smeared. As the frozen mix exits the freezer, it is immediately deposited into containers. Bluebell typically uses round paperboard cartons with plastic-coated interiors for ice cream, ranging from pints to half gallons. These cartons are automatically erected from flat stock, positioned on a conveyor belt, and filled via time pressure or piston-based filling heads. The heads are height adjustable and retract as the filling occurs to prevent air pockets or overflow. For varieties with variegates like fudge or fruit syrup, an additional stream is injected into the flow through a ribboning head, creating visible swirls as the carton fills from the bottom up. After filling, a lid is automatically pressed onto the container using pneumatic arms. The sealed containers pass through a rotary or linear check weigher that confirms the net weight is within spec. Underweight or overweight cartons are automatically rejected and sent to a separate path for inspection or rework. Accurate filling is essential not just for consumer expectation, but to ensure uniform freezing in the next step. The sealed containers are then conveyed into a hardening tunnel, which is essentially a long blast freezer where temperatures drop to 30 to 40 degrees Celsius. Inside, high-velocity fans circulate sub-zero air around the cartons, freezing the remaining liquid phase rapidly and reducing the core temperature of the ice cream to below, 18 degrees Celsius. This fast hardening process is vital to preserving the fine ice crystal structure created during freezing. The air jets are angled and modulated to provide even exposure and prevent frost buildup or warping of the cartons. The hardened ice cream containers exit the tunnel and move into the packaging area, where they are inkjet printed with date codes, flavor identifiers, and batch numbers. These markings allow full traceability from raw ingredient to final sale. Cartons are grouped into multi-packs using collators and tray packers, then boxed by robotic case packers into corrugated shipping cases. Each case is sealed with tape or hot glue, scanned for correct labeling, and palletized using robotic arms. Pallets are stacked in specific configurations that maximize airflow for cold storage and are wrapped in stretch film to protect against moisture and dust. Finished pallets are transferred to a holding freezer, typically kept between 20 and 25 degrees Celsius, where product is stored until it's loaded into refrigerated trucks. These cold chain logistics are essential to prevent thawing and refreezing, which would cause ice crystal growth and negatively affect texture. Delivery schedules are timed to coordinate with storage capacity and retail demand, ensuring that the product reaches shelves still within the optimal quality window. Every point in the process is monitored through industrial control systems. Pressure sensors, flow meters, thermocouples, and programmable controllers gather real-time data on mix temperatures, freezer speeds, air injection rates, filling volumes, tunnel temperatures, and even ingredient feed rates. This data is reviewed both in real time and after production to analyze batch quality, identify issues, and implement continuous improvement measures. Any batch that deviates from target parameters can be traced back through digital batch logs and ingredient tracking systems, allowing for full quality control. In terms of sanitation, the Bluebell factory uses CIP, clean-in-place, systems on all tanks, lines, and freezers. After each production cycle, a sequence of hot water rinses, alkaline cleaners, acid washes, and final sanitizers is circulated through the system at high velocity. The cycle times, temperatures, and chemical concentrations are controlled automatically, and post-cleaning validations are performed using ATP swabs or microbiological plate tests to verify the absence of residue or bacterial growth. Mix-in feeders and surface equipment are cleaned manually between batches, especially when allergens or strong flavorants are involved. The result of all these carefully engineered steps is a product with uniform texture, balanced aeration, clean flavor release, and reliable scoopability straight from the freezer. Whether producing vanilla, cookies and cream, or limited edition seasonal flavors, the factory process remains consistent. Transform a raw dairy mix into a frozen dessert that maintains its integrity from the first pour to the final bite. Ben & Jerry's ice cream begins its journey inside large stainless steel mixing vats where fresh cream, condensed skim milk, and liquid sugars are combined in tightly controlled quantities based on batch-specific recipes, with all ingredients pumped from chilled storage tanks through sanitary stainless steel lines that use flow meters and valve junction boxes to direct each liquid into the blending vessel in the correct sequence, ensuring homogeneity without introducing unwanted turbulence that might destabilize the emulsion forming at the early stages of mixture development. The mixing vats are equipped with high-torque agitators and slow-speed sweep arms that rotate along the inside surfaces of the tank walls, scraping the mixture and pulling ingredients from the periphery into the bulk flow, preventing solids like stabilizers or milk powders from clumping or settling during agitation. While shear heads built into the agitator columns create localized high-energy mixing zones that dissolve particles evenly and allow for a uniform dispersion of all dry and liquid components. Once all base ingredients are integrated, including emulsifiers that help bind the fat and water phases and stabilizers that give the frozen product its structural resilience, and slow down melting. During consumption, the liquid base is pumped through a plate heat exchanger that rapidly raises the temperature to approximately 82 to 85 degrees Celsius in order to pasteurize the product, which not only destroys pathogenic bacteria, but also activates certain proteins in the milk that contribute to a richer, denser mouthfeel when frozen. After this high-temperature short-time treatment, the base flows immediately into a second section of the heat exchanger, where it is chilled using a closed-loop glycol or ammonia refrigeration circuit that drops the temperature back down to around 4 degrees Celsius in a matter of seconds. And the pasteurized, chilled base is then directed into jacketed aging tanks, which are maintained at low temperatures and fitted with slow, continuous agitators to prevent the separation of fat from the aqueous phase and to allow the stabilizers and emulsifiers to fully hydrate over the course of at least 4 to 8 hours. This aging step is crucial in Ben & Jerry's production process because it prepares the mix to accept not only high levels of air during freezing, but also unusually large and dense inclusions such as brownies, cookie dough chunks, peanut butter swirls, and toffee pieces that would otherwise sink or damage the structure of a weaker base. The aged mix becomes a foundation that can support extreme texture variation without phase separation or flavor loss. Once the aging process is complete, the base is pumped into continuous freezers that serve as the mechanical heart of the frozen transformation. And here, the mix is cooled down to roughly 5 to 7 degrees Celsius while being whipped rapidly inside a horizontal freezing cylinder, where rotating stainless steel blades scrape frozen mix from the walls and simultaneously fold in filtered air through precision-controlled injection valves that regulate the overrun, which is kept deliberately low, around 20 to 30%, compared to typical supermarket ice cream, in order to preserve the ultra-dense, ultra-creamy signature texture that defines Ben & Jerry's. The low overrun means that each scoop contains more ice cream by weight and less air, which makes the freezing process even more critical because dense product holds and transfers thermal energy differently than aerated product. And the refrigeration system must respond in real time to flow rate changes, viscosity spikes due to mix-ins, and fluctuations in pump back pressure, all of which can affect the crystal size and final structure of the ice cream. At this point in the process, flavors and inclusions are introduced using multi-head ingredient feeders, which are synchronized with the flow of frozen base to meter out solid components like brownies, peanut butter cups, or cookie swirls at a controlled rate, using screw conveyors or belt-driven chutes to deliver exact portions into the stream without breaking or over-mixing the inclusions. The goal is to allow each piece to be suspended in the flow with minimal shearing or melting, preserving chunk integrity and creating the variety of texture that Ben & Jerry's is known for. For variegates like fudge ribbons or caramel swirls, the freezer's output is directed into a stream-splitting pipe system where the flow of base ice cream is divided and recombined with injected streams of liquid syrup using spiraled ribboning nozzles that introduce the syrup in twisting arcs, embedding them throughout the product without fully blending them in, and allowing distinct, bold streaks of flavor to appear visually and texturally when the final product is scooped or cut. The combined ice cream and mix-ins flow directly from the freezer head into automated filling stations, where pre-formed pint containers made of wax-lined paperboard or biodegradable composite are delivered via a conveyor, raised into position by a pneumatic lift, and filled from a piston dosing head that controls both the volume and height of the deposit to minimize air pockets while achieving consistent fill weights across thousands of pints per hour. And the filling process includes an overfill compensation stage where a small mound is left at the top to account for post-fill settling and shrinkage during hardening. Once filled, the pints move immediately to a lidding station where domed plastic lids are placed and pressed down using synchronized arms that index precisely with the conveyor's motion, ensuring a tight seal without deforming the container. And each lid is automatically printed with a batch code, timestamp, and flavor identifier using laser or thermal inkjet printers that connect to the plant's centralized batch tracking system, which records every data point from base formulation to final packaging for regulatory compliance and internal quality control. From here, the sealed pints enter a spiral hardening tunnel, which is a vertically stacked freezer that uses high-velocity, ultra-cold air blown at 30 to 40 degrees Celsius to extract heat quickly and reduce the core temperature of each pint to below 20 degrees Celsius within minutes. And this rapid hardening is necessary not just to finalize the freezing process, but also to lock in the structural suspension of inclusions and prevent large ice crystals from forming during storage. The airflow inside the hardening tunnel is controlled by a network of fans and directional baffles that ensure every container receives uniform exposure regardless of its position on the spiral belt. And exit temperature is verified using inline infrared thermometers or embedded probes that signal if any container is under-hardened and needs to be rerouted or rejected. After hardening, the pints are automatically collated into case packers that group them into cardboard boxes or cartons, often 6 or 12 per case, and these cartons are sealed with either tape or hot glue before being labeled with shipping codes and scanned by barcode readers that confirm destination, flavor mix, and inventory count before the cases are stacked by robotic palletizers that arrange cartons into pallet configurations optimized for freezer airflow and shipping stability. Each pallet is stretch wrapped with cold safe film, labeled with a master batch and product manifest, and transferred into deep storage freezers that maintain ambient temperatures between 25 and 30 degrees Celsius to prevent even microscopic temperature fluctuations that could cause texture degradation, especially for pints containing swirl-based variegates that are sensitive to heat migration and sugar inversion if stored improperly. Throughout the factory, process control systems monitor every mechanical and thermal parameter, from ingredient metering to packaging fill rate, using SCADA software that aggregates live data from flow meters, temperature probes, mixer speed controllers, and inclusion dispensers. And this information is used both for real-time error detection and long-term quality analysis that allows production managers to fine-tune the sequence of operations and ingredient preparation for future batches. Every component that touches the product is cleaned using CIP clean-in-place systems that route caustic and acidic cleaning solutions through closed-loop pipes, tanks, freezers, and depositors, followed by hot water rinses and sanitizer cycles that are validated through swab tests and chemical residue sensors. And lines are completely stripped and reassembled during allergen changeovers or seasonal flavor transitions to prevent cross-contamination. Ben & Jerry's factory process is designed not just to produce a high-quality ice cream, but to do so with a level of texture complexity and inclusion density that requires more robust mechanics than standard ice cream production. From the strength of pumps used to move mix with dense brownie pieces, to the tolerance of nozzles that must deposit syrup without clogging or over-mixing. Each component is selected and calibrated to handle the brand's commitment to chunky, swirly, intensely flavored ice cream with integrity and repeatability. Industrial ice cream production begins with the preparation of the liquid mix base. Raw ingredients used in the base include milk or milk solids, cream or anhydrous milk fat, sweeteners such as sucrose or glucose syrup, stabilizers, emulsifiers, and optional flavoring agents. Bulk liquid dairy components are stored in temperature-controlled stainless steel tanks connected to automated dosing lines. Milk fat content is measured using inline infrared sensors to meet formulation targets, typically between 8 and 12% depending on the product specification. Sweeteners such as granulated sugar or glucose syrup are stored in dry bins or heated tanks. Sugar is conveyed using auger screw feeders into blending tanks, while glucose syrup is pumped through jacketed pipelines at a regulated temperature between 45 and 60 degrees C to maintain viscosity. Stabilizers and emulsifiers such as guar gum, mono and diglycerides, or carrageenan are added in precise quantities, using dry ingredient feeders with load cell controlled hoppers. All components are blended in high capacity, jacketed stainless steel mix tanks equipped with high shear agitation. Mixing durations and shear rates are pre-programmed and adjusted based on batch size and viscosity targets. The mixture is heated uniformly to 70-85 degrees Celsius using indirect steam in the jacket to fully dissolve solids and activate emulsification agents. This thermal processing step homogenizes the mixture and ensures complete dispersion of the fat phase. The hot mix is then passed through a homogenizer at pressures ranging from 1500 to 2500 psi. This high-pressure two-stage process reduces the size of fat globules, creating a stable emulsion and improving mouthfeel and overrun stability. Homogenization is measured and recorded by inline pressure transducers and flow meters. Once homogenized, the mix is immediately cooled to below 5 degrees Celsius using plate heat exchangers. The cooled mix is transferred to aging tanks and held between 2 and 5 degrees Celsius for a period of 4 to 24 hours, depending on product type. During aging, the fat crystallizes and proteins hydrate, which enhances body, texture, and whipping properties. Aging tanks are equipped with low-speed agitators to maintain uniformity without incorporating air. After aging, the mix is pumped into continuous freezers. These machines are equipped with scraper blades and barrel chillers. The mix enters at 2 to 5 degrees C and is rapidly frozen as it moves through. The freezing cylinder cooled to approximately 20 to 25 degrees C using ammonia or freon-based refrigeration systems. The freezing barrel incorporates air into the mix during agitation. The amount of air added is called overrun, typically maintained between 60 and 100% by volume using controlled air injection valves synchronized with pump speed. The partially frozen ice cream exiting the continuous freezer has a temperature of 5 to 7 degrees Celsius and a semi-solid texture. From this point, the product flow diverges based on packaging format. For bulk containers, the ice cream is extruded directly into tubs or pails using piston or rotary fillers. For single-serve novelties or molded formats, the product enters downstream portioning or molding stations. In extrusion-based forming systems, the semi-solid ice cream is extruded through stainless steel nozzles onto a moving stainless steel belt, cooled to 40 degrees, using cryogenic cooling elements. The belt carries the formed shapes under a quick freeze chamber, where additional cold air is blown to firm up the shape. Inline sensors monitor form consistency and weight. Shapes are cut by ultrasonic or wire blades synchronized with belt movement. In molded systems, the ice cream is deposited into polycarbonate molds that travel on a carousel immersed in a brine solution held at 25 to 30 degrees. Product solidifies inside the mold within 8 to 12 minutes, depending on volume. Once hardened, sticks are inserted mechanically into the semi-solid mass using servo-driven arms. Demolding is achieved by briefly dipping molds into warm water baths and using pneumatic pistons to eject the bars. Fillings, inclusions, and variegates are added at multiple points. For layered products, rotary depositors add jams, caramel, or chocolate syrup between ice cream layers. Inclusion feeders dose chocolate chips, cookie pieces, or nut fragments into the flowing stream before extrusion using volumetric or gravimetric feeders. Variegates are added, using swirl nozzles or rotating spouts that inject sauces in spiral patterns into tubs. Enrobing stations apply chocolate coatings to frozen bars using curtain coaters or immersion tanks. Bars are transported on wire belts and pass through a curtain of liquid chocolate held at 30 to 35 degrees Celsius. Excess coating is blown off using air knives. Coated bars pass through a set zone where the chocolate is tempered and solidified using directed cold air streams. Toppings such as nut granules or cookie crumbs are applied to the wet coating via vibratory sprinklers before hardening. Once the shape is stabilized and the product fully frozen, packaging begins. Products are loaded into flow wrapping machines or form-fill seal machines. Printed film is drawn from reels, formed around the product, and sealed using heated jaws and pressure. Modified atmosphere flushing may be applied to reduce oxygen exposure. Each package is marked with batch codes and expiry dates via inkjet or laser printers. Packaged products proceed to check weighers and metal detectors for final inspection. Weighing systems use dynamic load cells to ensure each item is within +get 1% of target weight. Metal detectors with triple coil arrays scan for ferrous, non-ferrous, and stainless steel contamination. Rejected products are removed automatically from the line and logged in the manufacturing execution system. After inspection, individual packages are sorted into multi-packs or cartons using robotic collators and carton erectors. Units are loaded into retail-ready boxes, sealed with glue or tape and labeled with barcode identifiers. Cartons are stacked by robotic palletizers into programmed patterns based on load configuration and distribution route. Stretch wrapping machines secure pallets with film before warehouse transfer. In frozen storage, pallets are maintained at 25 degrees RC or colder. Pallet locations are mapped using barcode scanners integrated into warehouse management software. Products remain in frozen inventory for no more than the shelf life period assigned to each SKU. Rotation is enforced using first expiry, first out logic based on lot and production timestamp. The entire process is supported by centralized SCADA systems that monitor temperature, viscosity, pressure, weight, flow rate, air injection volume, and cooling intensity at every stage. Each unit of ice cream is fully traceable to its ingredient lots and production conditions through digitized batch records stored in the ERP system. The production of frozen yogurt in a factory begins with the preparation of the liquid mix base, which consists of dairy solids, sweeteners, live yogurt cultures, stabilizers, emulsifiers, and water. Each component is handled in isolated supply systems to ensure batch-to-batch consistency before integration. The mix formulation is calculated to achieve a target fat content of 2 to 4%, milk solids non-fat of 8 to 12%, and a final total solids content between 30 and 38%, depending on the product type. Bulk dairy ingredients, such as skimmed milk, whole milk, and cream, are stored in stainless steel, temperature-controlled silos or tanks held between 1 and 4 Allency. These tanks are fitted with slow-speed agitators to prevent fat separation and sedimentation. From the tanks, ingredients are drawn through dedicated pipelines with volumetric flow meters that measure and regulate dosing rates with tolerances within +0.2%. Sweeteners such as sucrose, glucose syrup, fructose, or high fructose corn syrup are stored in either crystalline form or heated tanks depending on their physical state. Crystalline sugars are conveyed to mixing tanks via screw feeders or pneumatic conveyors, while liquid syrups are pumped through heated, jacketed pipes to maintain constant viscosity. The addition rates of each sweetener are determined by pre-programmed recipes in the batching software and are adjusted in real time based on inline refractometers measuring total soluble solids. Stabilizers and emulsifiers such as guar gum, carrageenan, mono and diglycerides, or cellulose derivatives are pre-blended into dry mixes and introduced using vacuum powder hoppers into blending tanks containing preheated water at 60 to 70 degrees Celsius. This temperature is critical for full hydration and dissolution. Agitation is applied using high shear impeller mixers, ensuring uniform dispersion and hydration within 15 to 20 minutes. Viscosity is monitored continuously via inline rotational viscometers, and any deviation triggers automatic adjustment to the water feed rate or agitation speed. Once all ingredients are combined, the resulting mix is pasteurized using a continuous high-temperature, short-time HTST pasteurizer. The pasteurization process typically operates at 85 Celsius for 30 seconds to ensure microbial reduction without altering flavor or functional properties. The system includes balance tanks, timing pumps, regeneration sections, holding tubes, and cooling exchangers. Temperature probes and flow controllers verify that critical control parameters are met for every liter of mix. Any batch failing to meet time temperature integration is automatically diverted to a reject tank. Following pasteurization, the mix is homogenized in a two-stage homogenizer at pressures between 1500 and 2500 psi. The first stage breaks down fat globules to sub-micron sizes, promoting a stable emulsion, while the second stage disperses protein aggregates evenly throughout the mix. Homogenization ensures a smooth mouthfeel, prevents cream separation, and enhances the stability of the yogurt base during frozen storage. The homogenized mix is rapidly cooled to 4 degrees Celsius using a plate heat exchanger and transferred into agitated aging tanks. These stainless steel tanks have capacities ranging from 2,000 to 20,000 liters and are equipped with low-speed paddles to maintain uniform suspension without introducing air. The mix is aged for 4 to 24 hours depending on the formulation. During this aging period, fat crystallization and protein hydration take place, improving the whipping properties and final texture of the frozen yogurt. After aging, the next stage is inoculation with live yogurt cultures, a pre-prepared, freeze-dried culture blend containing specific strains of Lactobacillus, Bulgaricus, and Streptococcus thermophilus is rehydrated and activated in a sterile environment, then introduced into the aged mix in precise ratios. The inoculated mix is transferred to fermentation tanks equipped with temperature control systems. The mixture is held at 43 degrees Celsius for 4 to 6 hours, during which lactic acid is produced, reducing pH from above 6.5 to around 4.5. The acidification process causes protein coagulation, giving the base its distinctive yogurt flavor and slightly thickened texture. Once fermentation reaches the target pH, it is immediately halted by cooling the mix to below 8 degrees Celsius. This temperature shock preserves the live cultures and stabilizes the flavor. From here, the yogurt base may be held in intermediate storage for up to 24 hours before being processed further. If flavorings or colorants are required, they are added post-fermentation to preserve the viability of the live cultures. These additives are introduced through inline dosing pumps, controlled by magnetic flow meters for precise delivery. The chilled fermented yogurt mix is transferred to the continuous freezing units. These industrial freezers use scraped surface barrel designs, where the yogurt base is frozen while being continuously agitated by rotating blades. The barrel wall is chilled to between 20 and 30 degrees Celsius using ammonia or freon-based refrigeration systems. The rotating blades prevent ice crystal growth by constantly scraping the frozen layer from the barrel wall and remixing it into the semi-frozen matrix. During freezing, air is incorporated into the mix to achieve a desired overrun of 30% to 60% by volume, much lower than regular ice. Cream to maintain the dense, creamy consistency associated with frozen yogurt. The air injection rate is precisely controlled using mass flow controllers and synchronized with product flow rate. The resulting product exits the freezer at a temperature of 5 to 7 degrees Celsius and has a soft serve consistency. If inclusions such as fruit pieces, chocolate chips, or granola clusters are required, they are introduced at this stage using rotary feeders or auger-based inclusion systems. These systems are calibrated to dispense particulate matter based on mass or volume per unit of frozen yogurt. Inclusions are mixed gently into the flow using low shear blending heads to avoid damaging texture or shape. Forming and portioning depend on the packaging format. For cups and tubs, rotary or piston fillers dispense the frozen yogurt into containers on an indexed conveyor line. Fill levels are verified using laser height sensors or load cells beneath the filling stations. The containers are then lidded using pick-and-place robots, followed by heat sealing or snap lid application depending on the package design. For stick products or novelty bars, the yogurt is extruded into polycarbonate molds mounted on a carousel or linear track. The molds pass through a 30°C brine bath or air blast freezer for rapid hardening. Once the product reaches a core temperature of 18 degrees, sticks are inserted using servo-controlled plungers. The molded products are then released from the molds using brief exposure to warm water spray or ultrasonic demolding mechanisms. Products requiring enrobing are transferred to chocolate coating stations. Bars move on a mesh belt through a curtain of tempered chocolate or compound coating held at 32 to 34 degrees Celsius. Excess coating is removed using air knives, and toppings such as crushed nuts or cookie bits are sprinkled over the wet coating before it hardens in a subsequent cooling tunnel maintained at 15 degrees Celsius. Every unit, whether in cup, tub, or stick format, is passed through flow wrappers or form-fill seal machines. Packaging film is drawn over a forming collar, heat sealed along longitudinal and transverse axes, and printed with lot numbers and expiration dates using thermal inkjet systems. Products are checked on inline check weighers for mass accuracy, then metal detected using balanced coil systems capable of detecting contaminants down to 1.0 mmHg ferrous equivalents. Packaged frozen yogurt units are grouped into multi-packs or retail cartons using robotic pick-and-place systems. Cartons are sealed with hot melt glue and printed with barcodes and logistics identifiers. Palletizing robots stack cartons in programmed configurations. Each pallet is wrapped using rotary stretch wrapping machines and moved into blast freezers or deep storage warehouses. Frozen storage areas maintain air temperatures between 25 and 30 degrees Celsius, with controlled airflow to preserve texture and prevent ice recrystallization. Each pallet is tagged with barcodes that link to a warehouse management system, allowing full traceability of production date, ingredient lots, shift information, and packaging batch. The factory production of sorbet begins with the precise formulation of a base mix that typically consists of filtered water, fruit puree or juice concentrates, a combination of sugars, stabilizers, and acidulants. These ingredients are sourced in bulk and stored in isolated silos, refrigerated tanks, or powder silos based on their form and storage requirements. Before batching begins, each raw material is passed through automated intake stations where flow rate, weight, or volume is measured using mass flow meters or load cells to ensure formulation precision to the second decimal. The main batch tank is a large stainless steel jacketed vessel fitted with dual mode agitation, one high shear impeller and one slow speed anchor scraper to manage the simultaneous dispersion of powders and gentle circulation of the mix. The process begins by pumping deionized water into the tank. This water is processed through reverse osmosis filters to reduce mineral content and stabilize the flavor profile. Temperature of incoming water is held at 60 to 70 degrees Celsius to accelerate sugar dissolution and aid in the hydration of stabilizers later in the cycle. Fruit inputs, often high viscosity purees or concentrates, are pumped from cold storage tanks maintained at 4 rengangs. These tanks are fitted with bottom-mounted paddle stirrers to prevent sedimentation of pulp or particulate matter. The fruit component is introduced via jacketed stainless lines with rotary lobe pumps that preserve particulate integrity and ensure steady laminar flow. Inline flow meters measure delivery in real time, adjusting valves based on programmable batch set points. Sweeteners are introduced in multiple phases depending on their type. Crystalline sugars, such as sucrose or dextrose, are stored in bulk bag unloaders and conveyed to the tank using vacuum-driven feeders or screw. Augers, passing through sieve screens to remove agglomerates. Liquid sweeteners, like glucose syrup or high fructose corn syrup, are pumped from preheated tanks through jacketed lines at temperatures between 40 and 60 degrees Celsius to reduce viscosity. All sugar additions are monitored using an inline refractometer, which continuously reads the brix level and automatically adjusts feed rates to ensure consistency in total soluble solids. Stabilizers and emulsifiers, including locust bean gum, guar gum, or pectin blends, are pre-dispersed into a slurry using a high-shear induction system connected to a secondary mixing tank. The system uses a venturi-driven powder funnel that draws dry powders into a vortex of hot water, while shear blades break down clumps. The hydrated stabilizer solution is then metered into the primary batch tank over several minutes to allow for uniform dispersion. Viscosity is tracked by an inline rotational viscometer, while flow rate is synchronized with the agitator speed to prevent localized gelation. Acidulants are introduced once the temperature drops below 60 degrees Celsius to preserve their functional integrity. Citric acid and malic acid are most commonly used, added via microdosing pumps based on real-time pH feedback from inline probes. The typical pH target range for sorbet mix is between 3.4 and 4.2, depending on fruit type and desired tartness. Some blends may also include buffering salts or fruit-derived aromatic extracts, introduced in sub-gram quantities with gear-driven precision pumps. Once the mix is fully blended, the entire volume is passed through a plate or tubular heat exchanger for pasteurization. The product is heated to between 82 and 90 degrees Celsius for a holding period of 20 to 30 seconds using a hot water loop on the heating side of the exchanger. Flow rates are calibrated to ensure that each liter achieves the required thermal profile. Temperature probes at the inlet, outlet, and holding tube ensure compliance with the time temperature curve. Any deviation from set points automatically diverts the mix to a rework tank using pneumatically controlled valves. Following pasteurization, the mix is rapidly cooled to 4 degrees Celsius using chilled glycol in the final section of the exchanger. It is then pumped to aging tanks, insulated, vertical stainless steel silos with gentle agitators. The mix is held for 4 to 24 hours, depending on stabilizer type, allowing the hydration of hydrocolloids and maturation of flavor. During aging, key metrics including brix, viscosity, pH, and color are measured at regular intervals using inline and lab-based sampling. After aging, the mix is transferred to continuous freezers for dynamic freezing. These are horizontal barrel-type scraped surface heat exchangers with internal rotors spinning at high speed. The internal barrel is cooled by ammonia or freon-based refrigerant, keeping the wall temperature at 25 degrees Celsius to 30 degrees Celsius. The mix is pumped into the barrel at 4 degrees Celsius and partially frozen in under 30 seconds. Rotor blades scrape frozen mix from the walls, maintaining even temperature distribution and preventing ice crystal buildup. At this stage, air is injected into the freezing chamber to achieve controlled overrun. For sorbet, overrun levels are typically between 10 and 30%, maintained using mass flow controlled air injection, synchronized with product throughput. Air pressure, temperature, and flow rate are logged continuously. The exit temperature of the product from the freezer is typically 5 degrees Celsius to 7 degrees Celsius, with a soft serve consistency suitable for depositing. At the point of extrusion, some product formats receive inclusions or variegates. For inclusion, dry or semi-moist elements like fruit pieces, citrus peel, or coconut shreds are fed through a belt-based dosing unit with weigh cell feedback. The feeder aligns with the product stream and deposits inclusions just before it enters the filler. Variegates, such as raspberry swirls or mango sauce, are injected via multi-nozzle swirl heads using positive displacement pumps, synchronized with container indexing to create layered or spiral visual effects. The filling system uses rotary or linear piston fillers with programmable dose volumes. Fill heads descend into the container, release the product in a bottom-up motion to prevent air entrapment, and retract at the end of the fill cycle. Laser height sensors verify the final fill level to ensure consistency. For products with decorative topping, a secondary depositor adds surface sources, fragments, or textured swirls before lidding. Filled containers are sealed with pre-cut lids or heat-sealed films. Lidding stations use servo-driven arms and apply uniform pressure to ensure adherence. Date coding and batch marking are applied using thermal inkjet or CO2 laser systems immediately after sealing. Each pack is passed through a metal detector, which uses multi-frequency coils to detect foreign metallic objects within the sealed product. Immediately post-packaging, the product enters the hardening tunnel. This is a spiral or straight belt blast freezer, where ambient air temperature is held at 35 to 45 degrees Celsius. Air is circulated at high speed to ensure fast freezing rates. Dwell time inside the tunnel ranges from 30 to 90 minutes, and the goal is to reduce the core temperature of each unit to below just 18 degrees Celsius. Faster hardening reduces ice crystal size and improves long-term texture stability. Core temperatures are verified by infrared sensors or penetrating thermocouples on randomly sampled units. Hardened products are conveyed to automated carton packers. A vision system identifies each container's orientation and positioning. Robotic arms equipped with suction grippers or mechanical clamps group units into clusters and load them into pre-erected cartons. Cartons are sealed using hot melt adhesive or tape, then labeled using a print and apply labeling system. The label includes SKU identifiers, lot number, date, and logistics barcodes. Cartons are then routed to the palletizer. Layers of cartons are stacked according to a programmed pattern to optimize pallet stability and maximize transport efficiency. Stretch wrapping machines encase each pallet in multi-layered film with preset tension profiles to secure the load during transport. Pallets are labeled with SSCC codes and sent to deep freeze storage, where ambient temperature is maintained between 25 and 30 degrees C. Storage location is recorded in a warehouse management system using RFID or barcode scanning. Each batch of sorbet is traceable through electronic production records, linking ingredient lots, formulation parameters, processing times, and packaging data. Digital records include metrics for pasteurization, Brix values, overrun, pH, freezing rate, fill weight, inclusion density, and packaging inspection results. Production lines are modular and allow for multiple flavor variants and packaging formats. Line changeovers are performed by CIP, clean-in-place cycles, product purges, and recipe uploads via the SCADA interface. Automated valves and sensor diagnostics reduce downtime between batches. Lines may produce up to 8,000 litres of finished sorbet per hour, depending on viscosity, inclusion complexity, and packaging speed.